here is going to give us a lecture title, Models of Agglomeration, Growth and Evolution. Professor Kernan, please.
Yes.
Can you
Now,
start your talk?
So let me start. Sorry for the inconvenience. Thank Melanija for and organizers and Norbert for inviting me. I'm very far away at my country house, 100 kilometers from Paris. And now I have the pleasure to start my talk. I'm not sure, how much time do I have?
40 minutes.
30?
35 to 30 to 40.
Okay, good. Okay, so let us start. Sorry. Yeah, okay. So in this talk, I'll present a method of statistical analysis of dynamical changes and evolutionary trends in inorganic and biological systems. Biological, if I had enough time. And the tool is called stochastic matrices. And it is, these matrices are the ones that transform a set of probabilities, of discrete probabilities, into another set of probabilities. So let us see how it works. And the probabilities, of course, do not form a linear space. You cannot add them, you cannot multiply them, but they form a convex set in a linear space. But on the contrary, the stochastic matrices, they form a semigroup, as I will show you. So now the simplest stochastic matrix operating on a set of probabilities is, of course, 2 by 2. It is on 2 when you have just two possible issues, x and y, and you have the probabilities of these issues, px and py. Of course, these probabilities are positive or zero numbers normalized to 1. So there's only one parameter. And suppose that you have some probability distribution of these two issues, and then something happens that changes this probability. For example, you can throw the coin. If it is perfectly symmetric, then you'll have one probability, and it should be half-half, of course. And then suppose that your coin has undergone some deformation, and then you try the same experiment, and then you see that one side is getting more. So external influences can change the probabilities, of course. So now this change of probabilities can be described by an action of a 2 by 2 matrix. So we have new probabilities p prime x, p prime y, which are obtained from the other ones as linear. This is, of course, many problems are nonlinear, but the linear approximation works very well in most of the cases. So you see how it works. So now let us see what are the main features of a stochastic matrix. So you see that the new probabilities have to be normalized to 1. We have this equation, APX plus BPY plus CPX. So this is the new normalization. It can be written, it can be organized by separating PX and PY, the former probability distribution. And then you see that, of course, it should work for any combination of initial probabilities. For example, Px equals 1 and Py equals 0, or Px equals 0 and Py equals 1. And then you see the condition on stochastic 2 by 2 matrix is that in any column, it should be normalized to 1. So you see that this stochastic matrix has only 2 parameters. Now, this can be generalized for any dimension, any set of probabilities with n entries. So now there's another very important feature that can be, sorry, did I? Yeah, okay, sorry. So coming back to the 2x2 stochastic matrix, there is also one feature that is very easy to check, namely that at least one of the eigenvalues of such a matrix is equal to 1. It must have a unitary eigenvalue, and the proof in the case of 2x2 matrix, you just take the determinant and you see the equation. And of course, in this equation, it's very easy to see that lambda equals 1 is indeed a solution. There is another feature that all other solutions, they can be real or complex, but the absolute value must be always less than 1. This is very important because this means that whatever the probability distribution you start with, after some number of transformations with the same stochastic matrix, you will see only the asymptotic eigenstate of 1, because all other eigenvalues are being less than 1, the corresponding eigenvectors will be suppressed more and more. So let us see, for example, if you have 2x2 matrix, again, it has only 2 free parameters, A and B. And then if you want to have the eigenvector of the eigenvalue 1, it's very easy to be computed. You see Px equals B over 1 plus B minus A, and Py is y minus Px, of course, and this is like this. So we can always find out what is the asymptotic state. This is very important for other developments. So now this is the generalization, of course, for n by n matrices. Just all columns have B2 must be normalized to 1. This is the condition. And in some cases, one should use strongly stochastic matrices in which not only columns, but also lines, rows are normalized to 1. This is necessary if we put a Hermitian structure on the space of probabilities. But if not, only if we look only at columns, then we do not need the strong stochastic matrix. Just stochastic matrix is enough. And of course, it's easy to show that stochastic matrices have the group, one of the group properties. It means that a product of 2 stochastic matrices is also a stochastic matrix. This comes from the definition, of course. But they do not form a group. They form a monoid or semigroup because the sum of the stochastic matrices do not have the inverse. Not all stochastic matrices can have an inverse matrix. This is why it is not a group, but only a semigroup. So now one of the best ways to show how it works is the agglomeration. This is a model of agglomeration when you have some one-dimensional chains which grow by agglomeration. That means that elements of these chains are added on one or on 2 sides. For example, you can have a linear process with short and long segments. This is just like molecules or something like that. And then, for example, I show you how it grows. I take a segment with 3 items, SLL means short, long, long. Then I add a short and it becomes SLLS and so forth. I add on one side only. Here you see I'm adding on the right, but of course one can add on the left. It's just the same. And then it grows and goes to some statistics that is limit case, the infinitely, finally, the asymptotic state. So here, let us see how it can be described by a stochastic matrix. So of course, we can exclude or include, because in principle, if you have two kind of molecules, 2 kind of segments, which are called S and L, you can get, of course, 4 kind of pairs if you take the order. SS, SL, LS, and LL. But from the point of view of statistics, probably SL and LS is just the same. So, and one can also exclude or include some of the pairings. For example, one can exclude SS pairs if we want to get something that it should look like Fibonacci chain. Fibonacci growth, probably you know it well. This is not a stochastic matrix, but it is called inflation matrix because it multiplies the number. It acts not on probabilities, but on the segments themselves. So this is the matrix. You see, this is the matrix of inflation in the case of Fibonacci chain, which is also made of long and short segments. And then from a long segment, we get L plus S, and from a short segment is transformed into L. This is how it grows. And of course, the statistics is given by Fibonacci numbers. First, you have 2, 1, then you have 5 and 3, 13 and 8. You remember the law probably. Every next item is the sum of previous 2. This is the Fibonacci chain. And Fibonacci in 16th century, he found that this is how the trees grow. He understood that it cannot be just a geometric progression because it would be too much. So it is some kind of, so to speak, not geometric progression, but something in between from arithmetic to geometric. So this is the law of Fibonacci, and these are the Fibonacci numbers, and the statistic, the ultimate statistic, tends to the golden number, like this. So we let us suppose that we start to, the nature is not perfect, and usually it does not really go along the Fibonacci chain, but something close to it. So let us see how we can imitate the Fibonacci chain, but just by agglomeration, random agglomeration or not so random. So let us suppose that there's only contact interaction between short and long and short and long items. And if we want to imitate the Fibonacci chain, we have to exclude short because these do not appear in Fibonacci chain. So now suppose that we have a concentration. There's something like floating around a soup of these molecules, which one of them are, ones are short and the other kind is long. And then they agglomerate together. So if it were purely statistical, you'll get 1/4 of SS pairings, 1/4 of LL, and 1/2 of SL and LS. That is almost obvious. But apparently, to get a Fibonacci chain, it is not random. So let us see what can we see at the ends of the chain. Of course, normally we would see all kinds of pairings, but now in order to imitate Fibonacci chain, we will exclude these pairings. So this, for a physicist or for a chemist, one would say that the potential barrier for pairing of these short segments is infinite. So you exclude them and there is no SS agglomeration, only SL, LS, and LL. This means that the stochastic matrix would be 3 by 3. And of course, there are, if we put in some physics and chemistry, there are some Boltzmann factors which depend on temperature and on the potential barrier between the two kinds of molecules. So now let us see how it works. So we have admitted only 3 probabilities of these pairs, LS, SL, and LL. And then we can arrange the transitions, the agglomeration, one by one, is described by this matrix. You see, for example, in order to get an SL pair, it can be obtained only from this pair, because we put from the left, we put an L, and then we get SL. We cannot get it from this pair or from this pair. So this is why we have this factor, 1 minus C, because this is the concentration of S short segments. This is the Boltzmann factor, which takes into account the potential barrier. The same thing for obtaining LS, it can be obtained from this or from this configuration, and so forth. So this is the, but this is not yet the stochastic matrix. Why? Because the columns are not normalized, right? They are not normalized. So we have to normalize them to 1. Once we do it, that is what we get. And of course, this column is 1, 0, 0, because there was only one item. So once it is normalized, it gets 1 here. And these are the, and you see that also, if you look at it, you see that the two columns are identical. What you can get from L, this is normal. They are identical. This means that this matrix is singular. And it is singular, of course, because we have excluded the SS pairing. This is why it is singular. So now we shall introduce, because it is homogeneous, we shall introduce another parameter, which is just the difference of Boltzmann factors. And then it becomes even simpler. This is the stochastic matrix of this agglomeration, growth by agglomeration. And now let us see what is the characteristic equation. The characteristic equation is, as you see, of the third order, as it should be. And immediately we see that one of the eigenvalues is 0. This is because we excluded one of the pairing, SS. Now, the other two solutions, there must be a 1 eigenvalue equal to 1. And finally, another eigenvalue that is neither 0 nor 1, but something less than 1 in absolute value. So now it is easy to see what is the ultimate, the asymptotic probability to which any probability will tend after many, many steps of agglomeration. This is the probability. And of course, if you put it depends on mu, which is the difference of potential barriers between LL and LS pairings. And it depends on concentration of S and L segments. So for example, if you want to imitate the Fibonacci statistics, then we can solve the equation. Of course, it will be only approximate, because somehow we cannot avoid, for example, triplets like LLL, which are not in the Fibonacci chain, but we can go as close as possible to Fibonacci statistics. So now I'll skip this, because this is another model which is, I have not enough time. So I'll skip to another model, which is, sorry. Oh, God. Yeah, this is glass forming by agglomeration. It is also another application of stochastic matrices. So this describes in 3 dimensions the same idea that the clusters are forming in hot melt. When glass is formed in a hot melt, you get growth of local clusters, which when the temperature goes down, finally end up by forming an infinite network. So this is how it works. In the simplest, we'll take the simplest glass known, which is arsenic selenium. These glasses, arsenic selenium or germanium selenium or germanium arsenic selenium, the mix, they are used in photocopying machines. You can, if you open the machine, you will see them. They have the two important properties. Because of selenium, they are photosensitive. They can take on electric charge and lose this electric charge under the action of light. And then they have another property, that they are elastic. So you have huge sheets which are turning in your photocopying machine, and they systematically they go under the light, then they gather the ink in form of black powder, which goes where the charge is, and the charge is when the charge is left only when there was no light. So then you get the print. It's this fantastic use of glasses. So let me show you. Yeah, we'll make a model of arsenic, which has a valency, an atom of arsenic has valency 2, and valence of selenium, 3. Arsenic is 3, and selenium is 2 valenced. So here, this is a typical cluster. I have got it not for arsenic, but for germanium. It is germanium selenium. And whenever you have a cluster like this, you can see that there's something that you call bulk. And the atoms which are in the bulk, they are not available for further agglomeration because their valences are saturated. And on the rim of such a cluster, you have still some atoms which are available. Here's selenium, here's germanium with still one valence available. And so the model is exactly like what I showed you with the linear growth, but now it is, of course, in space. And you have two different items with different valences, the coordination number, and you have rim and bulk, and you have also Boltzmann factors, which give the potential barriers. Some of combinations, chemical links are formed more easily and some less easily. And of course, it all depends on. So here are the possible pairings. You see, here is the selenium-selenium potential barrier. We shall use this notation E2 minus epsilon. Selenium with arsenic is this, and arsenic with arsenic is E2 minus alpha. So we have now the valencies are also important, and we form a new stochastic matrix. This can be called the flow diagram, or you see how it works, that, for example, if you have one selenium atom available on the rim, this situation, we shall call it X. So it can be transformed either into X or into Y, according to whether a selenium atom comes to it or whether an arsenic atom comes. Here, the transformation, if a selenium atom is posed, it transforms into X and Z, because Z is this arsenic with only one valence available, or into Z and Y. And of course, here are the statistical factors which depend on the valence. For example, this here is 2 because a selenium atom has 2 valences, and 3 because of valence of arsenic atom. Now here you have 4 because selenium atom has valence 2, but it can come here or here. You have 2 possibilities. So all in all, it is 4. The same here is 6, and so forth. So now this can be encoded into a stochastic matrix like this, 3 by 3, because it gives you 3 possible, like here, 3 possible situations on the rim and the probabilities of getting them. So now this is the stochastic matrix. Again, we can put some simple expressions which will appear when we normalize it to 1, because this is not yet the real stochastic matrix. These are the factors that are inside that describe the process. And here, of course, once we normalize them, we get something like this, symbolically. And again, we can have one eigenvalue 1, for sure, and there are 2 other eigenvalues which are less than 1. So after many, many processes of agglomeration, these 2 eigenvalues will go to 0, because when they multiply and the corresponding directions in the probability space, they will go to 0, and only the asymptotic one will prevail. So the asymptotic eigenvector is this. It's normalized. And of course, it gives you the statistic of selenium and arsenic atoms on the rim. And if it is on the rim, asymptotically, it's the same in the bulk. So this is the stochastic matrix when you go to infinity. And while iterating many times, you get this expression. And the corresponding eigenvalues are, of course, in pure cases, for selenium, it's lambda 1 is 1. And then you get this type of distribution. And finally, there are realistic values of concentration less than 0.4. You have more selenium than arsenic. So these are different solutions. And finally, the very high temperatures, it goes to the asymptotic, which is exactly the same as it was in the soup, in the melt. So now what we can get, what physics can be get from this? The physics tells us that that glasses are extremely homogeneous. This means that in the bulk and in the melt, the concentration should be exactly the same. If it is the same, we can get a new equation, which is like a constraint. This equation is like this. You see that in the ultimate asymptotic state, Py to Px should be exactly the same as it is in the surrounding melt. This is the maximum homogeneity of glass. And this, because we had the temperature inside, the temperature when the glass is formed, it is called glass transition. So we get the following equation. And from this equation, we can get the dependence of glass transition temperature on concentration. And in particular, the slope of this curve. And the slope of this curve in general depends on this is for this glasses of 2 different valencies. For example, here it was arsenic and selenium, so it was logarithm 3/2. And in general, it is logarithm of 1 valence of another, which is very important because we see that if the valence is lower, then the slope will be negative. If the valence of the modifier is higher, then the slope will be positive. And here we have the experimental data of slopes of different glasses. There are 6 different glasses, and you see how fantastically this formula works. It's really, it's like an experiment. I think that 30 minutes are over, right? Melanija.
Yeah. Just a moment. I have to
So I
unmute
think that I can finish here. You
Yeah.
will have all of this. There's another application, very interesting one in heredity. This is for glass physics. There's another with heredity, which is very interesting, and heredity of blood groups, also described with stochastic matrices, but we have no time to discuss it here. But I will leave, of course, you have the...
You have for 5 minutes more if you want to use them.
No, so I'll just say a few words on heredity. Heredity is also, of course, it is pairing. It is history of pairing. You have two different in every, this is for Mendel's peas. He found the laws. It is fantastic because in 19th century, they did not know anything about DNA, about genes, but he explained the heredity by saying that there are some particles or factors which are transmitted from parents to children, and they go in pairs, and there's segregation, and there are some dominant and regressive features. He all observed it on peas, which were yellow and or green, and they had also, some of them were round and some of them were rough like this. And he described it, and of course, from modern point of view, it is exactly what happens, because we have the genes. Sorry, you have genes, you have alleles, which are typical dominant or recessive features brought by these genes. And this, for example, you have usually in each parent, for example, if you have just two alleles, which are here for the peas, it is yellow or green. So you can have two parents, when you have the pollinization from one flower to another flower. So the gametes can have YY and YY. So both are yellow, 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 yellow. So of course, from this, you'll have 4 yellow, yellow. You can have nothing else. But if one is yellow, yellow, another is yellow, green, then from this you get 2 children, which are either yellow, yellow, or either yellow, green. If you have one yellow, yellow, another green, green, then you have 4 children which are yellow, green. You have no other issue possible. You see? Then if you have 2 parents which are mixed, yellow, green, you can get yellow, yellow, or 2 yellow, green, the statistics, or 2 green, green. This is what happens. For example, sometimes you have people who are almost white, but they have some black ancestors. But if 2 such whites mate, some of the children can be very black, because it can happen. Or vice versa. They can be completely white, as you see, the same as with peas. And this, so this, you see that you have, this matrix will be, in fact, 3 by 3 or 6, let me see. Yeah, 3 by 3, because it is, we have only 3 types, YY, YG, and GG. So if we put this matrix and all these statistics, you'll have these factors. And once, when they are normalized, you get something like this. And this is the stochastic matrix that describes how the peas, yellow and green peas, how they will evolve after constant mating from one generation to another. And then finally, you'll get this kind of, which is quite easy to foresee, that 1/4 will be yellow, 1/4 will be green, and 1/4 will be half-half. One half will be mixed. This is pure statistical. But if there is some with, this is purely statistical mating. But with humans, it doesn't work like this because the matings are not completely random. So then they can, I show you, this is how the statistics evolve, going to the limit. And now the last thing I wanted to show, this is about blood groups, which are, you have A, B, and these are geographic, how they are differently distributed in different continents and different races and peoples. And this is O, and this is the flow diagram. And finally, there was a model developed by Ruben Aldrovandi, which of course describes the situation with stochastic matrix. It is quite complicated like this. It is 6 by 6. And also finally, it gives interesting results that show you it can be solved and show you what kind of barriers, what kind of non-statistical events had to play in order to give this very strange statistics that are real. They are completely different than random. Random statistic would be like this. You see, O group, OA, OB, AA, AB, and BB. But the real statistics are very, very far from that. So that means that during human evolution, there were very interesting and strange things that occurred that privileged some and suppressed some other groups. Well, thank you. This is enough, I think.
Thank you. Thank you, Richard, for your nice talk. As usual, we will have our section for discussion and exchanging comments at the end of this this part of the day, this conference part of the day, first part of the conference. Yeah. So our next speaker, it is my pleasure to announce our colleague James East, Professor James East, who obtained his PhD in pure mathematics at the University of Sydney in 2006. He joined Western Sydney University in 2011, where he is now an associated professor. James works mostly in algebra and combinatorics, but his interest in neighboring fields such as category theory, representation theory, geometry, topology, and philosophy. He is an editor for the Journal of the Australian Mathematical Society and currently holds in a future fellowship awarded by the Australian Research Council. I am invited James to give us talk titled presentation for temporally Lie algebras and associated monoids. James.
Okay, thanks very much. Thanks for the invitation and the kind introduction. I don't think I can share my screen at the moment because we have the previous slides.
Richard, please, can you stop sharing your slides?
Oh, I just don't know how to do it.
Okay, James, you can go on with sharing.
Okay.
It's okay?
Yeah, I think.
Oh, yes. Thank you.
Okay, can you see this now?
Yeah, we can see.
Oh, yeah. Fantastic.
Please go on.
All right. So, yeah, well, thanks again, and thanks to the organizers and the participants for this opportunity. This will be a talk about a paper that's soon to appear, and at the end, hopefully, I'll be able to talk about some other ideas that come up as a result of this. So this is about well-known objects, and in fact, the main part of this talk is about a well-known result as well, just a new proof of that. So let's start by talking about what it is this is all about. So the idea is of a tangle. So we fix an integer throughout the talk, n, to make sure everything is interesting. N is going to be at least 3. And we take 2 rows of points in the plane, 2 rows of n points, P1 up to Pn, etc. And everything is going to happen within the rectangle that these span. So let's call this R. After this page, everything will just be pictures. But so the things that we're looking at are built out of strings. So what's a string? It's just something, it's just a curve that stays within this rectangle. It joins 2 of the points like so. And we don't have intersections in the string. So it could be a straight line like this, or it could be a curved line like this one. And a string can join a point on the top to a point on the bottom, or it could join 2 top points or 2 bottom points. Doesn't matter. So there's another one. And a tangle, or an n tangle, if we want to specify the number of points, is a collection of n strings like this. So we fill up the rectangle with strings like that. There are 2 n points, n strings. So basically, it's a perfect matching of the points by planar curves. And the important thing is that there's no intersections happening here. Okay. Generally, we identify, excuse me, we identify a tangle like this one with anything homotopic to it. So anything that you can get by just sliding the strings around. Imagine the rectangle is water or something like that, and you've got these curves on it, and you're allowed to shake everything around. So that's another equivalent one. These guys are equivalent. Here's another one where we've let the strings get a little bit more wobbly, but you know they could get as wild as they want, and these are all considered equivalent. Okay, and once we know what a tangle is, the Temperley-Lieb monoid is just the set of all tangles, or all homotopy classes of tangles under a product that we'll talk about right here. So how do we multiply these things? Well, imagine we've got 2 tangles from a common Temperley-Lieb monoid. So we've got the same number of upper and lower points. Well, we compose these, or multiply them just like you might compose permutations, where you take diagrams like this, you stick them together like so, join the bottom of alpha to the top of beta, and then we look at the top row of points and the bottom row of points, and we see what things are connected. All right, so the first point here comes down, and through a sequence of edges, using edges from alpha and beta, it comes over to here, and so therefore in the product we have an edge like this. Okay, similarly, this one goes all the way from the top, it makes it through the middle, and then eventually gets to the bottom, so eventually we have this edge over here in the product. And you can show that this is an associative operation, so we end up with a semigroup, and in fact a monoid where the identity element will just be strings, all going vertically. All right, and this allows us to define the Temperley-Lieb monoid. To define the Temperley-Lieb algebra, we actually have to pay attention to the loops that might disappear when we make a product like this. So if I randomly drew 2 elements of Temperley-Lieb 1000, you have a much more complicated product, and there are probably lots of floating blocks, lots of floating loops in the middle of the picture. So we write m alpha beta for the number of loops removed, and this lets us define the Temperley-Lieb algebra. Most of the talk is not going to be about this, so I'll go over this definition a little bit quickly, but basically we have a field that's going to give us some scalars, and we fix a particular element of our field. Let's call that Q. And the Temperley-Lieb algebra associated to this field and this element basically is a vector space over the field with basis the Temperley-Lieb monoid. So think of this as linear combinations of tangles. Okay, just formal linear combinations. We might have 3 of this tangle plus 7.5 of that tangle, whatever. And basically, we use these basis elements to define the product in the algebra, where the product of diagram alpha by diagram beta is just going to be alpha beta formed in the way that I told you about it on the previous slide. But if there's any loops involved, we multiply this by a power of our fixed scalar. So in the previous example where there was one loop, alpha star beta will be q to the power of 1 alpha beta. Okay, so that's kind of the first thing that was defined in this field, the Templey-Lieb algebra. It's related to other algebras that existed before this, like of course symmetric group algebras, but also things called Brauer algebras, which arose a long time ago. That's basically like Templey-Lieb algebras where you don't care if there are crossings. But the idea here tends to trace back to this paper here by Templey and Lieb, of course. But interestingly, this paper doesn't mention this algebra at all. It doesn't seem to have these pictures or the generators and relations I'm going to mention. But this is where the ideas seem to originate back in. If I knew more about physics, I would probably understand why that is. But this thing was it was first seen in the context of physics, but it turns up absolutely everywhere in mathematics, and probably all the people here will have seen it in somewhere, some place or another. One of the biggest places it turns up in is knot theory, which is not a surprise given that we're talking about strings and things, but it turns up in biology, anywhere that you've got you know, knotting and things like that, like with DNA. But all these other more mathematical and computer science based fields. So this talk is going to talk about a paper, as I said, that will be appearing shortly in the Quarterly Journal. And the paper proves a result that was well known. And as the referee said in the report, the point of the paper is to prove something that everyone knows. And we'll see in a minute why you would want to do that. So what's this result that everyone knows? Well, it's the famous presentation for the Templey-Lieb algebra. I've stated the result for the Templey-Lieb monoid here, but we'll get to the algebra in a minute. Basically, it says that the Templey-Lieb monoid has a given presentation. Now, what's a presentation? Well, it's a list of generators and a list of relations. So the generators are these very simple tangles, and the relations are just a short list of equations. The basic idea is that these generators generate the whole algebra. So any tangle can somehow be constructed using these generators. What are the relations? Well, they're equations that happen to be satisfied by the generators, but they don't just happen to be satisfied, they somehow generate every equation that happens to be satisfied. So it's like a complete list of relations. So let's look at the relations one at a time. The first one says that each generator is an idempotent. So if we consider this relation, it says if I multiply EI by itself, I should get EI back. So let's do an example, E2 times E2. Well, what's the rule? We put the things together. We just look at the top and bottom rows, see what's connected, and this is all we're left with, which is just another E2. Okay, that's that relation. The next relation says that two different EIs, so an EI and an EJ, commute as long as the subscripts are far enough apart. Basically, that just means that I and J are not just consecutive. All right, and so E2 and E5, you can see that we get the same thing multiplying in either order. The interesting relation, or the most interesting relation, is when we take consecutive generators, and then we go EI, JI, simplifies to EI. And the explanation for this is basically if you follow the picture through, this line just goes all the way around past all of these hooks, and eventually if you just straighten that string out, you get just another copy of E2. All right, so those are the relations. Usually with these results, it's easy to check that the relations hold. It's harder to check that the relations generate every relation. But in this case, in fact, it's even not straightforward to show that these generators really do form a generating set. So if we randomly write down a tangle like this, how would we check that we can write it as a product of these guys? It's actually a fun exercise to write down a complicated looking tangle and see if we can decompose it. In this case, you can check it just by sort of following through the lines here, but it's not a trivial task. It's not kind of like permutations where you just look for the crossings and of course you stick transpositions wherever you see a crossing. But anyway, so just want to pay attention again to this first relation, because this is an instance where we had a loop in the middle. So if we wanted to interpret this relation in the Templey-Lieb algebra, we would actually think, well, okay, we've got E2 back again, but we've also got a loop here. So E2 squared should actually be Q times E2, Q to the power of 1, because we had one loop. And it turns out that if you add this Q, basically you turn the monoid presentation into an algebra presentation. So in fact, as long as you know the monoid theorem, you get the algebra theorem for free because of general results on what are called twisted semigroup algebras. All right, so who proved this theorem in the first place? Well, it's an interesting one because it's been floating around forever, really without a complete proof. The only paper that I'm aware of that says that it's giving a complete proof is this paper here by 3 authors who I believe are Serbian. And even in their paper, they have this discussion in the introduction about how, you know, the various facts are presented in various papers by various authors, but no one has proved anything. And they say that even in their own proof, there are some steps that they think it's probably hard to put down a complete proof for. So when I read this a long time ago, I thought it would be nice to try and give a complete proof, and that's the goal of this paper. So eventually it led to this paper, which I'll talk about shortly, and I want to give you just the idea of how I went about this. So the very high level strategy is simply, we have a theorem we want to prove. It has a presentation, and basically if you want some presentation, one way to do this is to just find any presentation whatsoever and come up with a way to turn that into the one you want. Okay, basically you just prove a lemma and then show that the theorem follows from that lemma. The slightly more detailed approach is that within the Templey-Lieb monoid are 2 submonoids, which I'd never seen studied before, and they somehow, in a very vague sense, capture half of the complexity of the full monoid. It kind of factors it into a left and a right half. We can then just look at the 2 halves separately. One is kind of the opposite of the other, so we actually really only have to look at one of these. Then we can somehow put these monoids together to find a presentation for the Templey-Lieb monoid that kind of has aspects of the structure of these 2 submonoids involved, and then turn this into the presentation that's more familiar. All right, and in fact, this is a variation of an idea that I've used quite a few times over the years. This paper here from 2006 has this little idea that is surprisingly useful in a number of contexts. So let's see what the idea is. So what are these submonoids? They're actually quite easy to explain. It comes with the idea of taking a tangle and kind of just looking at the top half and the bottom half separately. And we want to somehow form a monoid out of the top halves of tangles and another monoid out of the bottom halves. So I'm going to call a tangle bottom simple if the bottom row is as simple as it could possibly be. Okay, if you've got 6 lines going from top to bottom, they're going to land at the first 6 points, and the rest of the bottom is just a bunch of hooks like this, no nesting, nothing complicated. Okay, and we put all of these bottom simple tangles together into a set which we call LM. Okay, then of course we've got the idea of a top simple tangle, and the set of all top simple tangles is going to be called RM. These are going to be our monoids. Okay, and before we get to some kind of an argument to show that these sets actually are monoids, first of all, I'm going to explain how they split up the Templey-Lieb monoid into this sort of top and bottom half, or left and right half. It's not hard. You take an arbitrary tangle like this. We want to write it as a product beta times gamma, where beta is bottom simple, gamma is top simple. Well, the top half of beta is going to look like the top half of alpha. And since there are 3 lines going from top to bottom, the bottom of beta is going to look like this. Okay, and what choice do we have for beta other than just connecting those lines up? So that's what beta will be. And the same thing happens for gamma. We just look at the bottom of alpha, throw that into the bottom of beta, and complete that to a top simple element in the most obvious way we could. All right, so we have this factorization here. That tells us that the monoid itself is the set product of these 2 subsets. Okay, next we want to be sure that these things are submonoids. It turns out that they're anti-isomorphic to each other because there's an involution in the temporally lead monoid that sends one to the other. So somehow we only have to concentrate on one of them. Not only are they submonoids, but they have a fairly natural generating set. So if we look at just this element here, lambda I, it's got a hook at the ith position in the top row. And to be bottom simple, all of the strings go straight to the left. And then we've got this one hook left at the bottom. So this is kind of like the simplest bottom simple tangle you could get. Then we've got the rows which come from the top simple monoid. I'll just concentrate on the lambdas. How could we see that these things generate this monoid? Well, if you think of a bottom simple element like this, you can factorize this by, well, first of all, we count the hooks. There's 3 hooks at the top, so we're going to have 3 lambdas here. How do we know which lambdas? Well, we just look at the positions of the left sides of each hook. So we've got one in position 2, 3, and 5. Okay, so we're going to use those numbers over here, but in fact we go in reverse order. So we go lambda 5, lambda 3, lambda 2, and if you follow all the lines through, you will find that you get this picture here. So it's not obvious just looking at these how you're going to get long hooks. Okay, but the fact that these lambdas move strings along means that you can then use a short hook to combine it with these lines to end up with a long hook like this. Okay, this is not a proof, this is just an example. All right, to go in the other direction, to prove that any product of lambdas is bottom simple is by induction. A product of one of them just is bottom simple because you can just see it on the page here. And then inductively, you imagine you have a product of k of these guys. You assume the product of the first k minus 1 is bottom simple, and then you just look at cases as to where the next one fits in, whether the hook is between lines that already exist or whether it involves other points. And you consider these case by case and it works out. So we've got 2 submonoids. The whole thing is a product of the 2. So in some sense, they kind of are responsible for half of the complexity. This is not true structurally, and I've put these I put some egg box diagrams in to show the semigroup theorists. If we look at the full monoid on the left, when n is 1, there's nothing. When n is 2, there's almost nothing. It gets a bit more interesting when n is 3, where you can already see that the R monoid has fewer H classes. But once we get up to n equals 4, something interesting happens, which is that we suddenly already have a non-regular D class. Okay, we still have a chain of D classes though, but as we get as n gets bigger, this structure gets much more complex. So on the left-hand side, we just have a very nice chain of D classes. On the right-hand side, things start to get more complex. All right, and we can keep going. These are all drawn using GAP, for the computational algebra system. All right, so the slightly more formal idea of how we go about this is we take a tangle and we define 2 tuples, right? A top tuple, which is basically you find the left-hand endpoints of any hooks, like we did before, and we put them into a tuple, but for technical reasons, we make them start from the big number and go down. So 5, 3, 2 is the top tuple. Then, of course, we've got a bottom tuple, which in this case will be 7, 4, 1. All right, so this is some combinatorial data that we associate to this topological object, but it turns out that somehow the topology is completely described by this combinatorial. All right, so I hinted at this before. If you have a bottom simple tangle and you look at its top tuple, then this tells you the factorization of it in terms of these generators. Okay, and that has the effect that two tangles are equal. So these two topological things are equal if and only if they have the same tuples, which just tells you which points connect to which points, not how curvy they are or anything like this, or not which one goes around which other one, just which points get connected. And from this, it's possible to come up with a set of defining relations for the bottom simple monoid. We've got our generators, and I won't draw pictures of these, but basically these are the relations that you need to be able to turn any word into a product of this form that allows us to recover the tuple. Okay, we get the same sort of thing for the top simple monoid just by writing this presentation backwards. And then with a little bit more effort, we can combine these two presentations to give a presentation for the full temporally-lead monoid. This was never seen before because no one, I think, had looked at these generators. But we have this presentation which arguably is nowhere near as nice as the presentation that everyone knows. But once you've proved this, you have access to the other one by just transforming this into it. So once you've done this, I'll skip over the details. You then just rewrite the generators and relations into the result that's more famous. Okay. Now I do have a few other things that I can talk about, and I think I have sort of 5-10 minutes, so I'll go over these quickly. This will be sort of just some ideas rather than full mathematics. One is to extend this idea to so-called temporally-lead categories, which are also common tools. Another is to look at a thing that we're calling loopy monoids. This is sort of a fun name. We'll see if it sticks. But the temporally-lead category, it kind of comes from the idea of saying, well, okay, we've got this set of generators for the temporally-lead monoid. Okay, here is one of the generators for TL5. These are kind of like atoms. Okay, the monoid is built from these things. Okay, but just like with atoms, it turns out we can decompose these further. Okay, if you look at this picture, it's just 5 lines. Okay, why don't we treat the lines as separate algebraic things? So we give a name to them all. So we've got a vertical line, which we'll call I, because it looks like an I. Then we can call the top hook U, because it looks like a U. And then the bottom hook is called upside down U. And it turns out we can build our E2 out of these things with this funny kind of expression where the direct sum symbol, sometimes the direct product or the tensor product, means you take things and you stick them together sideways, right? Instead of combining them top to bottom, now we're combining them left to right. So we're kind of doing two-dimensional algebra here. So we start with an I, we throw in a U, then we throw in an upside down U, we throw in another I and another I, and we've created our E5. All right. So what we're actually doing here is we're doing calculations in a tensor category. And I won't go through the definition of the temporally-lead category, but basically any diagram like this with any number of upper points and any number of lower points, they don't have to be the same, can be built out of these simple things, stacking them horizontally and composing them vertically. And these are the defining relations. So it's worth looking at the pictures of these relations. So if you do a upside down U and then a normal U, that becomes a floating loop, which just disappears. Okay. If we do the U and upside down U in the other order, then we end up with this picture that has both loops. And we can do this by combining them vertically or horizontally in either direction. So it's a cool relation. This third relation somehow tells us how we can undo twists. And you remember we had a relation that was a little bit like this in the monoid, but we had a few more twists. All right. So it turns out that this relation here is, in fact, it's nice. I like it just because of how it looks. But in fact, you don't even need that because there are just basic tensor category axioms that imply this. So we can remove that. That's our presentation. Again, this was a result that's been quoted a million times, but never as far as I'm aware, concretely proved. But you can find a concrete proof for that in this other paper of mine, which is still in the refereeing stage. It's on the archive if you want there. It proves general results on categories and applies them to categories like the Templey-Lieb one and other ones. But let's now talk about the loopy monoids, which I think are a bit of fun. This is work together with Paul Martin, who's from Leeds. He's actually one of the two guys that independently came up with partition algebras, so he's a good guy to work on with this. And I started this project with him on the last time I was overseas, so quite a while ago. But the idea is that we saw the Templey-Lieb monoid. When we form products, we throw away loops. And in the Templey-Lieb algebra, we remember them by counting them. But the loopy monoid says, let's not just count them, let's let them actually be things, and not all loops are the same. So I'll illustrate this with an example, fairly simple example. So consider a simple tangle, alpha, and let's multiply it by itself. Okay, in the Templey-Lieb monoid, we stack it on top of itself, we throw away these guys, and we just end up with alpha. Okay, alpha is actually an idempotent. Whereas if we do this in the Templey-Lieb algebra, these loops stay, so we have q squared alpha. Okay, alpha times alpha is q squared alpha because there's two loops. All right, but let's look at another thing that will give us q squared alpha. So we just saw that alpha times alpha is q squared alpha. What if we throw some betas in between? So we're going to do alpha, beta, beta, alpha, and that looks like this. Okay, and what we see here is we still have a loop in the middle, but now we've got a much more complicated loop that turns into an enclosing loop. So we've actually got two loops nested, all right? But it's just alpha with two loops. So in the algebra, this is q squared alpha. So in particular, these two things are equal in the algebra. But if you look at the two pictures, you might wonder why they should be equal, because you can't transform one into the other. Okay, so another example would be if we calculate products like this one, alpha squared is going to be q alpha. We've just got one loop. But what if we again do alpha, beta, beta, alpha? Apparently ABBA is now back doing more music. So this is like an ABBA tangle. This is also q alpha. All right, but why should these be equal? Because you can't just transform the left one into the right one. You have to do something like move the loop into another dimension to move it across. So the loopy monoid takes these kind of diagrams looking like this, where we've got loops which might be nested, and it says the loops are actually part of the picture, not just, you know, a normal picture with 15 loops or something like that. And it says, well, let's see what we get when we generate using our standard generators, but we let the loops stay there. What do we get? Well, it turns out that you can define a good and a bad diagram depending on a horizontal line condition. Basically, you can't get too many vertical lines for any given horizontal line, but I won't go into the technical details of that. But then we ask, what are the relations? So two relations that obviously hold are from the original Templey-Lieb monoid. Distant generators are going to commute, and adjacent generators are going to have this untangling effect. But the generators are no longer idempotents because we're not allowed to just throw away loops. So I've deleted that relation. And the obvious question is that it? Is that now a presentation for the loopy monoid? And it turns out to be no, because here's a relation that isn't implied by these ones. We do something like E1, 2, 2, 1, 1, or 1, 1, 2, 2, 1. We'll just slightly move things around. That gives us two different ways to produce a diagram with two circles on either side of a string. Okay, that's a new relation. Is that it? It turns out that when n is 3, this does give us a presentation. Okay, but for n equals 4 and above, we have other relations. So this is two different ways to produce a single loop. You can break off a loop from strings 3 and 4, or you can break a loop off strings 1 and 2, and all you have is just a loop sitting there in the middle. We keep asking the same question, is that it? As far as we know, well, we don't know anything at this point about that. We've got some other relations we've come up with and managed to prove that they follow from these ones, but it's unknown at this point. So that's a place I'll leave the talk. It's ongoing work maybe one day I'll tell you the final answer. Thank you very much.
Thank you, James, for your nice presentation. And maybe next time in Niš, who knows?
Yeah,
Okay.
I hope so. It's a big pity I'm not able to visit.
I'm inviting Igor to give us a talk title, one related groups, monoids, inverse monoids, and update on the word problem. Igor?
Thank you, Melanija. So first of all, pleasure to be here in Niš. I'm physically in Niš right now. So sitting just to these wonderful people, a few meters from them. Strangely enough, I've been in Niš like a million times, but it's my absolutely first time on the Faculty of Mechanical Engineering, which is, well, unacceptable, and we must change that. But yeah, so I'm going to talk today about a topic in combinatorial group theory that is very closely connected to semigroups, as you will shortly see. And the conditions are perfect. I mean, I'm giving a talk with a glass of orange juice right here and a cup of coffee, which is, again, a first for me, rather than standing next to a projector or something like that. So quite pleasant. Here we go. So I'm going to share my screen now in a second. I hope you can see it. Okay, so as Melanija announced, one related groups, monoids, inverse monoids, and this would be hopefully a reasonably short update on the word problem and the status, in fact, of the problems surrounding the word problem of one related relations. So what I'm going to present is actually a joint work with Robert D. Gray, who was, well, we were hoping that he will be able to attend the conference, but quite recently he became a father. So congratulations to Bob and good luck with his newborn son. I'm here to represent our work in his name too. So without further ado, let me tell you about the word problem. James has done a great service to me by introducing the concept of generation of algebraic structures of a presentation. So it will be easier for me just to repeat these concepts. So assume we have given a group by some set of generators and some set of relations, which means that basically we are generating a quotient of a free group by a certain congruence, by a certain normal subgroup, or alternatively, you have a set of elements generating the group, and then every equation that you can eventually deduce within that group must somehow follow from the relations from the presentation. So we think of elements of G as words represented by this doubled alphabet. And then the word problem is the following algorithmic problem, which asks, given a word W over this doubled alphabet, does W represent the identity element in G? So this is a non-trivial question. For example, sorry about that. We will quickly rectify this. Yeah, good. So for example, if you are given one generator X and your relation is X to the 5th equals 1, that defines the cyclic group of order 5. And then clearly something like X to the 25 is a word that defines identity element. And you can ask similar questions for other algebraic structures as well, of course, for monoids, inverse monoids, and Lie algebras, associative algebra rings, so basically anything you like. Well, I will stick with semigroup-like structures. So the difference here is that you are given elements by words over an alphabet or a double alphabet in the case of inverse monoids. And now you're asking, given two words, you should decide whether they do represent absolutely the same element of the presented monoid or the inverse monoid. That's the word problem. So another basic notion is the notion of one related group. So as I said, this is just the quotient of the free group by the normal subgroup generated by the words, I mean, the elements represented by the words W. And then these are in terms of presentations, not in terms of structure of the group, but in terms of presentations, these are the simplest presentations one can think of. And then it's quite natural to ask, so, okay, is it true that these groups have a solvable world problem? And in a really famous result that somehow started it all, the whole modern combinatorial group theory, Wilhelm Magnus, student of Max, then proved that yes, every one-relator group has a decidable world problem. And this is a result which is really highly non-trivial. And along the way, Magnus developed really the basic tools of what is today the modern combinatorial group theory. For example, if you want to see what is the presentation for the free abelian group of rank 2, so the direct square of 2 copies of the integers. So you take 2 generators and you just say within the relations that, okay, the commutator of these generators is 1, which is absolutely the same as saying that xy equals yx. Or, for example, less trivially, the Baum's-like solitaire groups, which appear as fundamental groups of some really interesting objects in algebraic topology, such as the Klein bottle, or even more geometrically, the surface groups, so the fundamental groups of orientable genus G surfaces. So for the case when G is 2, the example of such a surface is shown here on the picture. So these are all one-relator groups, right? So it is quite natural when we have this nice classical and well-known textbook result on one-relator groups, it's quite natural to ask, okay, so what happens to monoids then, for example? And it comes across as quite surprising that the analogous problem for monoids is unsolved to this day. This is an open problem. Truth to be said, many things are known about this, and Adyan was the mathematician, the famous Russian algebraist who penetrated the most within this problem. So the word problem for a one-relator monoid is decidable. For example, if you're talking about a special monoid, a monoid that is defined by a relation of the form u equals 1, which is not something that all one-relator monoids satisfy. Okay, within groups, when you have something like u equals v, you can transform this within the realm of groups into the form uv inverse equals 1. So basically every presentation is of the form something equals 1. But this is of course not true in monoids. You don't have inverses in general. So this is quite a special case, an important one at that. Or when both u and v are non-empty, however, they have different initial letters and different terminal letters. That case is resolved by Adyan as well. And then much later, because Adyan's proofs was really difficult to read, to say the least, then it was quite challenging to find simpler proofs, right? So this is, Zhang was particularly successful in this because his proof of the special monoid case is quite elegant and short, in fact. Okay, so further down the road, Adyan with his student Academician in '87 proved that basically the whole one-relator problem for monoids can be reduced to this special case when you have a presentation of the form, a relation of the form ASB equals ATC, where B and C are different letters and S and T are some words, and of course the dual case. So the question is, why the inverse monoids? Where do they come into the story? Well, the thing is that in the groundbreaking paper of Ivanov, Margolis and Mikin in 2001, they noticed this interesting little thing. Should we be able to prove that the word problem is decidable, so algorithmically solvable for all special inverse monoids? So inverse monoid given by presentations W equals 1. And I again must draw the attention that, again, not every inverse monoid presentation is of this form, even though we have inverses, but it is no longer true that XX inverse equals 1. It's just some general idempotent. in the inverse realm. So where W is a reduced word over doubled alphabet. If we are able to prove this, then automatically it is true that the word problem is decidable for every one relator plane monoid. So there is some secret connection, obviously, between special inverse monoid and ordinary monoids. That's what Ivanov, Margolis, and Mikin discovered, because they have proved that this monoid from the Adian-Oganessian result basically can be embedded into a certain inverse monoid that is given by one relation only. And this is the relation that is shown on the screen. A as B, C inverse, T inverse, A inverse equals 1. Okay, so what's the situation? The situation is, as long as we are confined to the special presentations. Well, okay, in the group world, every presentation is special. Everything can be written as something equals 1. And that the word problem is decidable in that case, that's exactly what Magnus proved in 1932. Then in 1966, Adian, and later on many other authors, proved that this is also true. I mean, the solvability, the algorithmic solvability of the word problem for special monoids. And then what about the special inverse monoids? That's the question. Well, one would expect that this trend would continue, right? And this was in '87 explicitly formulated by Margolis, Mikin, and Stephen as a conjecture. So the question was, is it true that every inverse monoid, which is given by one special relation, has a decidable word problem? And surprisingly enough, my dear friend Bob proved that the answer is no. And this proof and this result is so good that last year it was published in Inventiones Mathematicae, so one of the most prestigious journals in the world. So that the result is there exists a one relator inverse monoid with a special one defining relation that has an undecidable word problem. And this result, as it turns out, follows simply from the existence of a certain one relator group and its finitely generated submonoid, such that the membership problem of that finitely generated submonoid is undecidable. So within a group, you have not a subgroup, but a submonoid, so a subset closed for multiplication, whose membership problem is undecidable. And so I'm briefly now going to explain what is the membership problem and the related prefix membership problem that I want to talk about a little bit more. So, okay, let G be a general finitely generated group and assume we have a finitely generated submonoid given by, I don't know, a finite set of words that represent elements of G. So the membership problem from M then asks if the following decision problem can be algorithmically solved. So the input is a word, and then the question is, does this word W represents an element of the group that belongs to the given submonoid M? Now, you can ask this for general submonoids, or you can ask this for some quite special monoids, such as the prefix monoid. So consider, for example, this one relator group G that is defined by the relation W equals 1. And not so much for the group, but actually for the very presentation which defines the group. Because, you know, one and the same group can be presented in many different ways. So every presentation basically will have its prefix monoid. So you take all the prefixes of the word W, and then with these prefixes, I mean, by the elements defined by them, you generate a submonoid. And this is the prefix monoid of the group presentation. That would be the correct thing to say. And now the prefix membership problem for the one relator group asks if the membership problem from this particular monoid is algorithmically decidable. So the question is, given an element of G, can you decide whether it can be written as a product of prefixes of W? So some elements can, some elements cannot, and you need to distinguish between the two in an algorithmic way. Okay, here is an example. Consider the group G that is generated by two elements, A and B, and say this is the defining relation, which basically says that A and B commute. So this is simply a very simple group. It is the square of the integers. And then the prefix monoid is the monoid generated by, as we said, the prefixes. So A, AB, AB inverse. And then it can be seen that this is basically the monoid generated by A and B, because simply A, B, A inverse, if you consider the given relation, that is simply the same thing as B. So the prefix monoid problem here basically asks, can you recognize the positive words? I mean, the elements defined by positive words. And sure, fair enough, you can, because in Z times Z, you simply can reduce every word to a normal form of the like A to some power of B, and then you check whether these powers are simply positive. So here is a concrete example. You are given a random word, that's fine, but once you commute everything, you eventually conclude, well, this is just A to the 4 times B, and yes, these exponents are positive. Whereas in this other case, when you commute everything, you conclude that you have business with the element A to the -2, B to the 7th, and this is not element of the prefix monoid. So there you go. And now the problem which we wanted to consider is it true that every one-related group has a decidable prefix membership problem? And if the answer is no, well, then can we at least describe the words W for which this is true? What we are doing is we are trying to stretch further and further the Magnus result. Okay, by Magnus, every one-related group has a decidable word problem. And then we try to increase the level of difficulty. We're asking more and more difficult decision problems than the word problem itself. But the reason for this is not just pure curiosity. I will say later what motivates this actually. So I just want to mention, and I will quickly go through this, that the prefix membership problem is proved to be okay for several special cases. For example, if you have an idempotent word in the free inverse monoid. If this is strictly positive, I will not even go into defining what this means, but there is some quite simple combinatorial definition what it means that the word is strictly positive. Then if the word defines certain adient type of Baum's-like solitaire type groups, some small cancellation type conditions, well, this already involves geometric group theory. So there are special cases when W's will work. So why is all of this important? Well, this is because we want, well, to study the word problem for inverse monoid defined by one special relation. And another result of Ivanov, Margolis, and Mikin in the very same 2001 paper is, well, when this inverse monoid is E-unitary, and I will shortly explain what this means, then the word problem for the inverse monoid question is absolutely the same as the prefix membership problem for the one-related group defined by the same relation. So what are the E-unitary inverse semigroups? Intuitively saying these are the good guys of the inverse semigroup theory. As we all know, in semigroup theory, inverse semigroups have a natural inverse semigroup order, and one condition of being E-unitary is, well, if you sit above an idempotent, you're an idempotent yourself. Or if you consider the minimum group congruence on the inverse monoid, so the minimum congruence, which has the property that the quotient is a group, then it should be idempotent pure. Meaning if you're related in this relation to idempotent, then you're an idempotent yourself. And there are like a million equivalent conditions for this. And the important example is here. If W is cyclically reduced word, which means that within W, you will not find adjacent letter and its inverse, and also the first and the last letter of W are not mutually inverse. So when this is the case, then necessarily this monoid is E-unitary, which is an important example, of course. You get quite a lot of inverse monoids in this way. So what we did in our recently published, in fact, it appeared this summer in paper in the Transactions of the American Mathematical Society, we considered, well, quite a number of cases for the prefix monoid problem for several one-related groups. And our strategy was first to obtain some very general theorems which involve the two basic constructions of combinatorial group theory, well, the free amalgamated products of finitely generated groups and the so-called H&N extensions. And then these general theorems, which basically say, okay, we have these two constructions starting from free groups, and what submonoids can we claim that are certainly decidable, that they have decidable membership problem. And then we are trying to fit the prefix monoid into these general results. That's what we did. Here is a sample of such a result. So we have several, I don't know, 4 or 5 general theorems, but here is just the first one. Suppose we have an amalgamated free product of two groups, H and K, amalgamate, and I will give you a picture of this, amalgamated over a common subgroup L. All of them finitely generated, fine. And then assume that the membership problem for L, for the common subgroup, is decidable both in H and K. And then furthermore, let M be a submonoid of our group such that it contains whole of L, the whole amalgamated subgroup. Then the intersections of M with H and K are finitely generated as monoids. And these two sets basically generate together the whole M. Then we require that the membership problem for M intersect A in H is decidable, and the same for K. And then if we have all these conditions met, then we can claim that the membership problem for M in G is decidable. So the image is like this. Basically, you have two groups, H and K. You have a common subgroup in the intersection, that's the red part. And now you have some monoids, some finitely generated submonoids sitting within G. It contains all of L, as you can see, but it has some potentially bigger intersection with H and K, which is respectively, I'm hoping that that's what you're seeing, blue and green. But also M has some considerable part outside the whole thing and within the amalgamated free product. And with these conditions, we can claim that M has a decidable membership problem within G. So, okay, to show you the applications, and that's what I intend to do within the next 10 or 15 minutes, I must quickly explain what conservative factorizations are. So again, we are returning to the realm of one-related groups. And with respect to this word W, which defines the presentation, we consider a factorization. So we just split up the word W into several parts and define this submonoid of G, P of W1 to WK, basically corresponding to the factorization. And we generate this, then again, not using the mouse, and that's my curse right now. Okay, here we are. So we consider the prefixes not of the whole thing, not of the whole word W, but we consider the prefixes of the pieces, WI. And with these prefixes of the pieces, we generate a submonoid. So it is fairly easy to show that this monoid contains the prefix monoid, because sure enough, every prefix of W can be written as the product of prefixes of these pieces. Of course, you take a product of some pieces and then a prefix of some piece, say WL, I don't know. But sometimes, if for just a fluke, it can happen that equality takes place. This can happen quite easily so. And when this happens, we say that the factorization we have started with is conservative. So conservative because it doesn't change the prefix monoid. You just slice up the word W, and then you just take into account the prefixes of the pieces you have obtained. And this suffices to preserve the prefix monoid. So these factors, as I already did, will be called pieces. Okay, so there are several methods to find conservative factorizations of a word, and one is contained in the early papers of Adyan. This is the well-known Adyan overlap algorithm, and this is based on the observation that if you have alpha beta and beta gamma as pieces, so you have two pieces that have in common suffix of the one and the prefix of another, then all three factors here, alpha, beta, gamma, by themselves are pieces. For example, take this presentation, and then you end up with the conclusion that this factorization A, B, C, D, A, B, C, D, C, D is conservative. And another much more recent method belongs to Bob, and now our colleague, originally from Serbia, Novi Sad, Nick Rushkuc, who is now a professor at the University of St. Andrews in Scotland. It's based on the Benoit theorem, which is a well-known theorem in theoretical computer science. It states that all the rational subsets of infinitely generated free groups have uniform decidable membership problem. So, for example, this method, the Benoit method, suffices to show that in this presentation, what I have given here by different colors is definitely a conservative factorization. And that will be important in another example that comes up shortly. Okay, so here is our first application, for example. Suppose we have a one-letter group and we are working with a conservative factorization of the corresponding word. And let this be the set of pieces appearing in this factorization. I did this because simply the same piece can appear multiple times. So say if one and the same piece appear 10 times, I don't want to take it into account 10 times. I just want to have a set of pieces that are involved. And assume that for each piece, there is a letter which appears exactly once in UI and nowhere else. So somehow these letters AI are the unique identifiers for these letters. So therefore the unique marker letter theorem, therefore the name. If this happens, then we can prove that the group defined by the relation W equals 1 has decidable prefix membership problem. And here is an example. So start with this group, which has at first sight a really horrible presentation. This is a long word, but then pretty quickly the Adyan overlap algorithm will show you that this, what is given in dark and light blue, is actually a conservative factorization. And you can now see that there are only two kinds of pieces involved here. Well, AXB and AYB. And sure, indeed, X and Y are the unique marker letters because X appears exactly one in the first piece and does not appear in the other, and Y the other way around. So we can now claim from our theorem that this group defined by this presentation has a decidable prefix membership problem. Also, this group I was talking about just a couple of slides earlier, where the Benoit algorithm discovers a conservative factorization. And you will notice now that you don't have actually the unique marker letter property here, because just you're looking at the pieces and there is no letter that appears only once in each piece, but nowhere else. However, what you can do is a little transformation. Hail to the Tietze transformations. Okay, so once you write up this presentation a little bit different, just by inserting a little bit extra, these pairs of A inverse A, you end up with factorization like this. And now, if you consider the pieces, which are ABA inverse, ACA inverse, A and AD, and basically that's it. It is now true that every piece has a unique marker letter, B, C, and D, respectively. And then you can show that, of course, that's the danger. Once you change the presentation, there is the very prominent danger that just by doing that, you will actually change the prefix monoid. But in this particular instance, this does not happen, luckily. The prefix monoid remains the same. And this is the infamous O'Hare example, which the question whether this particular group has a decidable prefix membership problem stood, as you can see, for 32 years open, so third of a century. The name comes from, by the way, from O'Hare Airport in Chicago. I mean, John Meekin and Stuart Margolis were working at the Nebraska University at the time, and they were waiting for a connecting flight. And well, two mathematicians, what you can do, they end up doing mathematics while waiting on a plane, and they come up with this pretty unpleasant example that couldn't be resolved for 33 years, and Bob and I succeeded to do that. Okay, so second application, disjoint alphabets theorem. It says, again, you're considering a conservative factorization of a word that defines a one-related group. You consider the pieces, and now you're requiring that basically the alphabets over which these pieces happen are disjoint. They have no letters in common, and then you can claim, of course, that the corresponding group has a decidable prefix membership problem. So here is an example. Again, the Ardian overlap method will produce this conservative factorization, which involves only two types of pieces, ABAB and CDCD. And as you can see, the alphabets are disjoint. There are no letters in common, so we can claim that G has a decidable prefix membership problem. And then as a third application, which basically harks back to the H&N extension construction, assume you have a one-related group when within the defining word, you have a certain letter that has t exponent sum 0. For example, here is one such word, 80 square, a squared, t to the minus 3. When you just add up the exponents of 3 of the letter t that appears here, it appears to be 1. So this is the situation we are seeking. And then by the observation on Moldavanski, the following then exists. Once you have this situation in your group, you have another one-related group with a relation that is simpler, with a relation that is characterized by a word which is shorter. And then you have two subsets of the new generating set X dash, which form basis of three subgroups of G dash. You have an isomorphism between these three groups, such that G is basically isomorphic to the H&N extension of G dash with respect to this isomorphism. And then our theorem goes as this. If this is all met, and if this is a notation we are working with, if you start, for example, with G dash being a free group itself, and the W has this combinatorial property of prefix T positive, which means whenever you take a prefix of W, then the sum of exponents of the letter T within it will be positive. Once this happens, we can prove that G has a decidable prefix membership problem. Well, our result is a little bit more general than this, but it would require much more technicalities, and I don't want to do that right now. So anyway, further applications then, based on this, we can prove that the prefix membership problem is decidable within the following types of groups. For example, the cyclically pinched groups given by presentations of this type, which would then involve all the surface groups. Well, for the orientable surface groups, it was already known that they have prefix membership problem algorithmically solved, but we somehow recreated this result in a quite different way. But also we are able now to prove the same result for the non-orientable surface groups, which are also very important in differential geometry. Then, for example, the conjugacy pinched groups, which include all the Baumschlag-Soritter groups, some groups of adient type, and so on and so forth. So for the finish, I would just end up with a negative result, showing that hope, proving that all the one-related groups would have decidable prefix membership problem is basically false. We have managed, based on the Bob's paper in Inventiones, to find a reduced word. So not just any word, but a word which does not contain any cancellations in it, such that the corresponding group defined by the relation W equals 1 has an undecidable prefix membership problem. So it is a proper open problem. Okay, describe the words W, which has the property that they induce one relator groups that have one decidable prefix membership problem. That is quite a challenge. And we would very much like to know, and we are also very much hoping, if at least all the cyclically reduced words are among these words, because reduce are not, as we can see from the above theorem. Thank you very much. I have managed to do this, wow, in 36 minutes. Way to go.
Okay, thank you, Igor, for your nice talk. Thank you for being with us together.
Well, I had a question to James East, but he's disconnected.
No, he's connected.
Yeah, but
I can see.
Oh, thanks. I was wondering whether your model could be generalized if the sites were of, say, two different kinds, red and blue, or and how to treat it stochastically or probabilistically. Would it be interesting? I think it would.
There's lots of different versions of these sort of things. I wouldn't be surprised if there was one of the kind that you're talking about, but I don't know of it myself. But these things turn up all over science for various reasons. So probably, I'd think.
Yeah, I think that it could be applied to the kind of models I was describing, you know, the agglomeration by lines or by bulks. It's very similar somehow.
Yeah, I don't know the physical connections, but it comes up in statistical mechanics. So
Yeah.
probably exactly what you're talking about.
Yeah. But if you think of DNA, how it is, how it's assembling the two lines, there are 4 different types of sites. It's very, very similar.
Yeah, I think Igor and I spotted some article by some authors who were looking at temporally lead monoids in connection with DNA somehow.
Well, yes, there is a group working at the University of South Florida in Tampa, and they are working on applying generally diagram monoids, but mostly temporally lead monoids to well, modeling in biology, especially in DNA recombination and modeling stuff like that.
No,
So,
thank you.
Okay. Some other comments, questions?
And you don't get that it separates consecutive ones. So you have to do a little bit more work to find a nice family of identities where it's sort of satisfied by UTN, but not satisfied by UTN plus 1. And that's what Tom did. Yeah.
So it follows in particular from that and the fact that the plactic one contains UTN, it follows that the infinite plactic doesn't satisfy.
Yes, it does. But it's kind of easier to show that actually, because you can prove that the infinite rank plactic monoid can't satisfy, you can prove that you can't satisfy anything of length less than n. And so the infinite rank one can't satisfy anything at all. Yeah, so that makes it easier. But yeah, that is a consequence. And yeah, there are some kind of strange things that happen with these low rank versions. So UT2, the variety generated by that is the same variety as the variety generated by the bicyclic monoid. It's the same variety as the variety generated by the plactic monoid of rank 2. For UT3, it turns out to be the same variety as generated by the plactic monoid of rank 3. So you might hope that that was always true, but I don't believe that it is. But you might also wonder, is there a nice monoid or a nice semigroup, nice combinatorial thing that generates the same variety as UTN? And I don't know the answer to that.
Are there any other questions? if there is not, then we can go on a lunch break. And I invite you to join us at 3 o'clock to attend colloquium on application of semigroups within logics. Till then, enjoy your lunch. And thank you for all presenters for their really nice talks.
Thank you.
Thanks.
That I see recording in progress. Okay, got it. Good. That should also be possible to follow by people who are not familiar with the topic. So I will be very basic, very introductory. I don't want to worry the experts. And what I will do is to show a little bit the diverse landscape of what has been called substructural logics in the literature. So what are they? Where the name comes from, based on some common proof theoretical features that can be found in them. I will briefly mention the main modern, mostly semantical perspectives on their study, and I will say a little bit about a logical approach based on connectives that I have proposed together with my colleague Peter Sintula. So we know that already with antecedents going back far away in time, but mostly during the 20th century and up until today, non-classical logics keep emerging time and time again from a variety of different motivations, logical systems that deviate one way or another from the well-known classical logic, from, say, completely mathematical reasons, or because of philosophical motivations or more applied motivations coming from the fields of computer science, linguistics, etc. People have proposed a real diversity of different non-classical logics. And inside this complex world, there are some subfamilies that have come to be called substructural logics, but they are very different. First, let me point out to historically who they are. And I think they can be more or less classified in mostly 4 different groups. First, historically, we would have the relevant logics. First, because the historians like to, really search back for early examples, and they found that as soon as early as the 1928, the Russian logician Orlov proposed a system that later turned out to be identified as one of the relevant logics. But mostly, this is a stream of research that starts in the 60s with the works of people like Anderson, Belknap, Dunn, and others that follow a mostly philosophical motivation to study logics of entailment that in some way address the well-known paradoxes given by the classical definition of material implication. So they want to have logics in which every implication has only a relevant premise, not unnecessary premises. This means that they will have to get rid of some of the classical rules, such as the weakening rule. Then independently of that, another well-known family of logics that starts with the work of Joachim Lambeck in the 58, motivated by linguistics, in that case, by the study of combinations of grammatical categories in formal, but also in natural languages. So like when we analyze syntactically the structure of a sentence, and we want to see how its different pieces are combined, we realize that these combinations obey some rules, but not some other rules. So he proposed a very weak system of logic, actually more than one, in which some of the usual rules of classical logic again would fail to account for this particularity of the combinations of grammatical categories. So for instance, he would have a non-associative conjunction, also non-commutative. So the order matters in sentences, the way we associate parts matters, etc. Then there is another group of researchers, mostly starting from the foundational work of Ono and Komori, the Japanese mathematicians in the 85, that started studying logics without yet another classical rule, the contraction rule. mostly a mathematical line of research that focuses a lot, but not only, on the algebraic semantics of those logics, also possibly without other well-known rules such as exchange or weakening. And finally, another important independent family in this complicated landscape would be linear logics that usually are thought to start with the work of Jean-Yves Girard in the 87, in that case coming from the area of theoretical computer science, in which he proposed systems that would take care of what happens in computational processes, in which one has to keep track of the resources that are being used, computational resources such as memory space, computing time, etc. And again, here, the order of the usage of those resources may matter, or it may matter that if we have to use some resources to obtain some result, then maybe if we add more resources, we don't obtain that result anymore. So maybe also the weakening rule can be problematic. Definitely the contraction rule can be problematic because we will have to count how many times we use every resource. So again, we'll have to get rid of contraction. So what do these systems have in common? Why are they called substructural logics when they come from so different motivations and they are studied from different points of view and different approaches and different tools, etc.? Well, you already see, by the way, I'm speaking, that they do have in common this lack of classical properties that I have been mentioning. Let's try to make this a little bit more precise and justify their name. To do that, we have to go to the sequence calculus presentation of classical logic or of intuitionistic logic. If you want, I wrote the classical one here, given already in the 30s by Genzen. The system LK, let's take the system LK of sequence, which are pairs of two sequences of formulas, one in the left, one in the right, separated by some syntactical symbol that here I depict by this triangle. And then we give axioms and rules in a proof system. So an axiom that says you can only derive phi, triangle phi, and then some rules, the so-called structural rules, because they just give us ways to operate with the structure of those sequences of formulas, but they don't refer to the connective that actually appears on those formulas. So the rules of exchange say that the order doesn't matter. You can exchange the order of things on the left, also on the right. Usually we'll have this duality all the time, rules to do something on the left-hand side and rules to do something on the right-hand side. The rules of weakening on the left, it says you can add some formula phi that wasn't there on the left side. Also, you can do it on the right, add some new formula phi. A rule of contraction that says that if you have something repeated, you might as well have it just once on the left and on the right. The rule of cut still is structural, does not refer to any connective, and it accounts for the intuitive notion of transitivity of the entailment. And then, of course, a collection of axioms and rules that have to tell us how to deal with the specific connectives that we'll have in our language. So rules for the constants of truth and falsity, actually axioms, they have no premises, and rules for conjunction, disjunction, implication, to introduce those connectives on the left and on the right for each of them. I will not read them in details because that's not the point here. Just to remind you, probably most of you already know that this possible presentation of classical logic exists, and it has been indeed very important. It is a presentation of classical logic. It can be shown by means of the following result. A sequence of the form, you have a collection, a sequence of formulas phi's on the left and formulas psi on the right, is derivable in that sequence calculus, even only if the formula that collects the conjunction of all the things on the left, implying the disjunction of all the things on the right, is actually a valid formula of classical logic, a tautology of classical logic. So then, as an immediate corollary of that, we obtain that for a finite set of formulas, gamma has phi as a consequence classically, even only if the corresponding sequence gamma phi is derivable in the system. Okay, that was just a recap of Genzen's presentation of classical logic. But now, more interestingly, for the topic of today, we can replace the rules that we have seen for the connectives. For instance, we could take the rules I have just shown before for conjunction on the left and on the right, and write something else instead, which, if we look at it, also looks very intuitive and very natural. For instance, this introduction on the left that tells you if you have the formulas phi and psi, you may just put their conjunction there on the left. Or that if you derive from one set of premises phi and from some other set of premises psi, if you unite the premises, you may derive their conjunction. Those are rules that are different from those that I put originally, but they can shown to be equivalent. So you can have the system with one pair of rules, or with the other pair of rules, you have the same. You have still classical logic. You can do similar things and give equivalent rules for the introduction of disjunction. So those instead of the original ones. You could also change the rules that govern the behavior of the constant of falsity, the constant of truth, and still remain equivalent. But what is important is that in order to obtain these equivalents, we are always using the fact that we are in a context that already contains the structural rules, in that case of weakening and contraction. If we are allowed to use weakening and contraction, we can show, I'm not showing you the details because of the lack of time, but we can show that those presentations of the connectives are indeed equivalent. So then the question is, what happens otherwise? What happens if we remove weakening and contraction? Then the equivalence doesn't hold anymore. So what we may say is, well, maybe then what's happening here is that we are describing two different possible behaviors of conjunction. We would have the original conjunction that was obeying the original rules on the left and on the right. And then I could have another connective described by the alternative rules, left and right. So the prime rules. And then let's just use a different symbol to refer to that. So we would have another thing that behaves like the conjunction of classical logic in the aspects described by these rules, but it's not equivalent to the other one. And the same with the disjunction, with the constants. So what we are obtaining here is a weaker logic, because we have removed rules. We have got rid of the rules of weakening and contraction. It's weaker, but in a way it's more expressive because it has more connectives. And I haven't written this, but it would be something similar even for implication. If we remove the rule of exchange, I could have rules describing the usual rule describing one implication, but also some alternative rules describing another implication. So it was actually a mathematical logician of our host country today, the Serbian logician Kostadocian from the University of Belgrade, who in the 1990, observing this that I just explained, proposed the all-encompassing label for these diverse families of logics, I believe in a lecture in Tübingen. He said, well, let's just call them substructural logics because they are obtained by removing the structural rules. And then we see all in the same light. So then relevant logics typically turn out to be logics that could be presented by agains and calculus without weakening. Lambic logic could be presented with agains and calculus without exchange, without weakening, without contraction. Linear logics and its variants could be obtained from removing the contraction from the agains and calculus. That's, of course, an informal characterization, so it has invited several mathematical precisifications and corresponding streams of research, which I dare to very roughly characterize in just two groups, which are not so focused on this proof theoretical perspective that I was just mentioning before, based on presentations on agains and calculus, but actually they are more focused on semantical approaches. But of course, they don't reject also the proof theoretic approach, which is also very well developed and very useful in many aspects. And for the lack of better names, I would just call them a stream A and stream R. Stream A, standing for algebra, would be the natural continuation of those pioneering works of Ono and Komori starting from the 85 that I mentioned before, which takes these substructural logics as a very interesting mathematically motivated family of non-classical logics that typically receive a semantics based on classes of residuated lattices. We will see a lot about that in the next talks of this session. The motivation is mainly mathematical, as I say, focused on the algebras, but not only. They will also employ techniques from proof theory. They will also have some forms of relational semantics, topological interpretations and dualities, etc. So good sources of knowledge on this stream of research are the books written by Galatas and others, by Pauli. I will give the references at the end. The other stream, very roughly speaking, would be the one that I would call R. In principle, R for relevant, because it's, again, the natural continuation of the works started by Anderson, Belknap, and others in the field of relevant logic, retaining those original philosophical motivations of trying to understand entailment in the idea of relevant implications. So without weakening, taking care of the strange, so avoiding the perceived strange features of the material implication. They are typically studying systems that are in principle introduced by some form of proof system, and then giving them relational semantics, which are generalizations of the Kripke frame semantics that we know very well from intuitionistic and modal logic. Books on this area are the Restall, Anderson-Belknap, done, again, references later for those interested. So yeah, R for relevant, but also R for the emphasis on the relational semantics. I understand that most talks of today will mostly focus on the first of those two choices, the algebraic side of things. Let me now say a few words of another possible approach that I would like to explain a little bit. Approach based on connectives. Because so far, I have been referring, and this is not strange, this is what usually you encounter in many discussions of substructural logics historically, as systems that are somehow defective. No, it's kind of a negative way of introducing them, because they are introduced as something that does not satisfy certain properties of classical logic, the structural rules. So something obtained by removing properties from very strong classical or intuitionistic logic. We could also propose a reverse approach in which we start not on the top, but on the bottom with something very weak, but still very natural, and keep adding more and more properties according to our needs for modelization. So what I'm going to do is to speak in the way of Hilbert-style systems instead of Gensen-style sequent proof systems, because of the higher versatility that the Hilbert-style systems have from a theoretical point of view. Also because of the more direct link that they have to the algebraization, to the algebraic semantics. Then I will be therefore describing connectives according to their intended behavior in terms of Hilbert-style axioms and rules. And we will start by what some people like to argue could be the main connective, the main logical connective, implication. The main one, not the only necessary one, implication. So a possible approach to that was already suggested in a work by Petr Cintula in 2005, calling a logic weakly implicative if it has what he called a weak implication. What is that? It's a binary connective, maybe primitive in the language or maybe definable, such that it obeys the following very basic properties every implication we should think should obey: reflexivity, modus ponens, transitivity, and when symmetrized, this congruence property with respect to all other connective of the language. So if phi and psi are equivalent with respect to implication, because phi implies psi, psi implies phi, they can be equivalently substituted in the context given by any other connective present in the language. If you do that, okay, that's the syntactical approach, the syntactical presentation. If you do that, then it has a very natural semantic reading, because the models of that, in algebraic logic, we would like to have algebraic models, but we are very general, and sometimes we have to have something more basic than just algebras, what we call matrix models, algebras with a set of designated elements, call it F. Those are pre-ordered for a weak implicative logic. They have a pre-order that is very naturally introduced in the following way. Two elements of the algebra, A and B. A is less or equal than B, even only if the algebraic interpretation of their implication is a designated element of the set F. That's a pre-order always, thanks to the syntactical properties of implication. If we, moreover, require this pre-order to be actually an order, so to have the anti-symmetry, then what we obtain is a subclass of these models that actually give a complete semantics for the logic. So those are the logics of order in this sense. Now, about implication, but what about the other connectives? We may want to have more expressive power than that. So yes, we can add other connectives, conjunction, disjunction, that also we behave according to order theoretical properties, maybe, expressing the order in terms of lattice properties, so behaving like a lattice meet and a lattice join. Maybe we want to have extremes for this lattice order, a maximum element top, a minimum element bottom. Maybe we want to have a junction for our conjunction, then we just write this rule. If we have phi and we have psi, then we have their conjunction. Maybe we want to have another constant that may be the same as the top, but not necessarily, having the push and pop properties. So from phi derive 1 implies phi and vice versa. So a constant pointing at the minimum truth, so to speak. And we may want to have the very famous residuation property that allows to put together premises of consecutive implications. So premises of nested implications. So we have phi implies another implication that starts with psi. I would like to write this equivalently just in terms of one implication that has the conjunction of those as the premise. So the internal premise psi conjuncted with external premise phi. We are very general. We want to work with logics that don't have all those properties, in particular, don't have a change. So the order of those premises will matter. So if I want to reverse things, maybe I cannot in general, but one trick to do that is to make the language more expressive and introduce another implication connected, this funny arrow, which allows to change the order at the price of changing the implication inside. And they all bound together by this residuation property. And we may have other properties. Let me just move on because the time is running short. Then, a possible notion of substructural logic from this point of view in this context would be the following. We will call a logic substructural if it has at least an implication with this very minimal reasonable behavior. It is a weak implication, so the properties we have seen before, reflexivity, modus ponens, transitivity, symmetrized congruence, and moreover, the following two properties of suffixing and prefixing. So giving an implication, we can add premises in front, that's the prefixing, or conclusions behind, that's the suffixing, because those are properties that we encounter in virtually all substructural logic. And the logic given by just these very basic properties is already logic identifiable in the literature that has been considered substructural one. So let's take it as the weakest logic of our approach. And we call it LL arrow because it's actually the implicative fragment of one of the first systems introduced by actually Lambeck. The Lambeck, the non-associative, very basic Lambeck logic, just the implicative fragment of that would be presentable by identity, modus ponens, suffixing and prefixing. So it is a weakly implicative logic with suffixing and prefixing, because the suffix and prefixing also give the symmetrized congruence property, and you can derive easily the transitivity. So then, equivalently, we could say that the logic is substructural even only if it expands this basic one, and it keeps the implication being still a weak implication. Okay, but that's only in the very basic language of having just implication. Let's see how we would add this richer stock of connectives. Yes, we may want to do what I was saying before, to have the second implication to account for the lack of exchange and still have the residuation property, I could add all those axioms and rules and have also all the axioms and rules accounting for the lattice behavior of conjunction and disjunction, and also accounting for the behavior of the top and bottom connective, and also for the behavior of the constant one with the push and pop. All of this, just write it down on a long, nice Hilbert-style proof system and get a logic that will be the least substructural logic in which the connectives have this desired behavior, Let's call it just SL for substructural logic, for the lack of a better name that we have not found in the literature. And then this would be a solid foundation to build upon to keep adding more properties to retrieve other substructural logics. So other substructural logics may be obtained by adding other desired properties. So maybe we want our conjunction to be associative. So I just put axioms for associativity. We want to have exchange, which is equivalent to having the commutativity of the conjunction. We may want to have contraction of consecutive premises, consecutive implications with the same premise, which is equivalent to the idempotence of conjunction, etc. So then we obtain a hierarchy of logics extending SL by adding some of those properties, associativity, exchange, this I and O property for 1 and for 0 being the bottom and the top, etc. And in this family, we would retrieve most of the logics that we have in the literature. So Lambeck logic is already this very basic one, SL in the full language, or the famous full Lambeck logic that it's already associative would be the logic SLA in this presentation. With exchange, we would retrieve the typical family of linear logics, extending this one, and if we have exchange and contraction, we would identify many relevant logics living here and above. Then in this framework, it's also very natural to go to the algebraic counterpart, because we have at our hands easily the notion of algebraic implicative logic, which is exactly the notion of algebraizable in the sense of Bloch and Pigozzi. SL can be proved to be that, so are all of its extensions and well-behaved expansions with more language. What happens here is that the reduced models have the filter equationally definable, and the algebra is actually residuated lattice ordered unital groupoids. Typically, we will add more than that. We will want those groupoids to be semigroups, to be associative, actually, because they also have a unital element monoids. And those are usually called bounded residuated lattices. We'll see details about that in the next talk by Paolo, and also in the subsequent ones. To see more about this approach, you could go to our just published book with Peter Sintula about weakly implicative logics, and all the references that I have been giving, these important books on substructural logics that you can find for more details. Thank you very much for your attention.
Thanks, Carlos. I mean, you finished early, and so this allows me to start earlier and be a little bit less rushed than in expressing my, in giving my talk. Now, I should introduce myself, but Norbert has already done that, so maybe that's not necessary. But what do I want to talk about? Well, okay, Carlos explained you how we have a bunch of logics, I mean, that can be defined substructurally in many different ways and from many different points of view. And the algebraic semantics of these logics are, to me, very, very interesting. Also the relational semantics, but this is not my field. So I will talk about the algebraic semantics. And I will focus mainly on the process of algebraization. So what does it mean that a certain class of algebras, most of the time a variety of algebras, a class closed under homomorphic images, subalgebras, and direct product. So what does it mean for this class of algebra, this variety, to be the equivalent algebraic semantics of a logic? That's what I'm going to explain you. Actually, this is going to be the final part of my talk. the initial part of my talk, I'll try to talk a little bit about the structures, right? Because I mean, you know, after all, the title of this colloquium is, you know, application of semigroups in logic. And of course, I mean, here, what do we have? Well, we have residuated lattices, right? And residuated lattices are lattices in which there is a monoidal structure underneath. And this monoidal structure, actually, it gives you the real interesting part, right? Because, you know, lattices, we know what they are. They are partially ordered set in which the infimum and the supremum of any finite set exist. In particular, it exists the infimum and the supremum of the pair AB, and so we can define them as A join B and A meet B and A join B. So A join B is just the supremum of the pair AB, and A meet B is just the supremum of the pair AB, and we can regard lattices as commutative idempotent monoids, and this is it actually. I mean, and they give you an order structure. Now, on this order structure, we can sort of, you know, superimpose a monoidal structure, and of course, we will have a lattice ordered monoid. In fact, the correct name for residuated lattices would be residuated lattice ordered monoids. But we don't like long names, so we tend to sort of compress them, right? And so residuated lattice is an algebra that is a lattice. It is also a monoid. And well, we have two operations that can be considered the right and left residuations with respect to the product, right? So we have a residuated monoid, basically. That in general is not commutative. In general, one is not the uppermost element of the lattice. There not need to be a bottom element. If there is one, it's okay. There may be a bottom element, but it's not necessarily constant like one. I mean, one is a constant operation. So algebraically speaking, it belongs to the type of the algebra. If we want to the bottom to be a constant and to belong to the type of the algebra, then we have a different situation, which is closer to the algebraization of full Lambert calculus, as Carlos explained you before. But I mean, what are these guys? Well, they are a variety of algebras. I mean, which means that they are the class of models of an equational theory. So, or equivalently, they can be axiomatized by equations, right? I am not going to give you the list of equations because it's long and rather uninteresting, but they are very rich structures. I mean, they satisfy a lot of equations, a lot of algebraic things. And for instance, I mean, the order can be defined not only by join and meet, but also by both residuations. X is less than or equal than Y if and only if X backslash Y backslash X is greater than 1, if and only if X slash Y is greater than 1. And this backslash operation is monotonic in the first argument and anti-monotonic in the second argument. And the slash operation is monotonic in the second argument and anti-monotonic in the first argument. And we have a bunch of equations holding. Here I have 3 examples. I mean, this one here, you have already seen it. If you remember in Carlos Noguera talk, is he used a different symbols, right? He used the arrow for the backslash and the squiggly arrow for the slash. And of course, I mean, here everything is backward for the arrows. I mean, this is very confusing, I know, but I've struggled with this notation myself a long time. But I mean, this is the accepted notation in the field. So I, even though I think it's not the best possible choice, I'll have to use it anyway. But I mean, it took me a long time to figure out these things. But I mean, and I mean, we have other equations, right? I mean, really many of them. I mean, it's, as I told you, even at the very basic level. So if you don't ask anything but these 2 properties, they are very rich structures. I mean, this doesn't mean that they are very easy to study, on the opposite, but still, there are a lot of things that hold the residuated lattices. Now, the other thing is that they are ubiquitous. I mean, they appear everywhere. Okay, historically, what is a residuated lattice? Is the abstraction of the structure that one can impose on the lattice of ideals of a commutative ring with units. Because I mean, this is a very well-known fact. If we denote the usual multiplication of ideals by simply juxtapositions, then this set has a largest element, always. I mean, provided we have a unit, but okay. And this element is usually denoted by I colon Y. And of course, this gives you an implicit definition of residuation. It's just, you know, I arrow J, I is just the largest element of this set. Of course, here I'm assuming that the ring is commutative. So clearly, if this operation is commutative, then these two operations coincide, right? Because if this is commutative, they're defined exactly in the same way. So other example, very classical structure, a lattice ordered group, an L group. An L group is an algebra that is a lattice and a group, and the multiplication is order preserving. Again, we can define this by equations, but it's not very important. But of course, I mean, I can define the backslash as x, y minus 1, and the slash as y to the minus 1x, y inverse x. And in this case, G becomes a residuated lattice. But of course, I mean, you can do better than that, right? Because every relatively pseudo-complementary lattice can be given a structure of a residuated lattice. For instance, an I-thing algebra is a residuated lattice, right? Why? Well, because of the same reason basically as for ideals, because this set has the largest element. And this is just the definition of pseudo-complementation. So again, relatively pseudo-complementary lattices are residuated lattices. And this is a stranger example. Take any monoid and take two subsets of the monoid, two elements of the power sets. And we define the multiplication, you know, just in the usual, you know, ring way multiplication, just all the products from X and Y. And if we define the backslash and the slash in this way, then the power set of a monoid is a residuated lattice. We can construct many different examples of this kind. I mean, if you want to have a, you know, there are several places where these examples can be found. One is this book here, which is Residuated Lattices and Algebraic Glimpse at Substructural Logics that, you know, Carles has already in his references. But I'm particularly fond of all the examples you can find in Nick Galato's PhD thesis, which is available online. And there is really a bunch of examples of residuated lattices from everywhere. Okay. Now, two observations. Not any lattice can be given a structure of a residuated lattice. So you cannot just take a lattice and hope to make it into a residuated lattice. Well, because it's easy to prove that if a lattice has a minimal element, if a residuated lattice has a minimal element, then it must also have a maximal element. So if it has a bottom, then it has a top. It follows that if a lattice has a bottom but not a top, then it cannot be given a structure of a residuated lattice. However, residuated lattices are general enough in this sense that any lattice can be embedded in a residuated lattice, even in a residuated lattice with some special properties. And any monoid can be embedded in a residuated lattice as a monoid. Okay, so residuated lattices are very general, both as lattices and as monoids. Now, what about the structure theory? Okay, the structure theory, I mean, as I told you, these are very nice. I mean, they are congruence permutable. So and this is the Maltsev term, they are congruence point regular at one, and also congruence distributive because they have lattice term. In terms of general algebra, they are the nicest possible structures you can have. Okay. But what does it mean? It means that they have a good theory of ideals. In other words, the congruences, I mean, so the equivalence relations that are preserved by the operations, they are compatible with the operations, okay, are completely determined by certain subsets, exactly like it happens in groups, right? Congruences and normal subgroups in a group can be identified. And this role in residuated lattices is played by congruence filters. Now, what is a congruence? What is a filter of a residuated lattice? Well, of course, first is a filter of the lattice structure in the classical sense. I mean, it's a subset which is closed underneath and closed upwards. But it has also to be closed under multiplication because we are in a residuated lattice, so we have a monoidal structure and we have to take care of it as well. Now, not surprisingly, how can we identify the congruence filters? Well, the congruence filters are just these guys, right? So the one then can be written in this way for some congruence. So we can actually prove that if we take this A plus, which is just the filter generated by 1 in the lattice, and we consider A plus over theta, where theta is a congruence in the classical sense, I mean, just the union of the congruence classes, right? This is always a filter, and a filter is a congruence filter which is equal to A plus over theta for some congruence. And now we have a perfect correspondences between congruence filters and congruences, right? And they are, of course, they form algebraic lattices, I mean, all the usual stuff, and they are isomorphic as algebraic lattices, and because there are, these two maps here are mutually order preserving, I mean, okay? So this is a very common situation in algebra, right? We have this, you know, the congruence lattice is actually isomorphic to some other lattice that is obtained in a different way. Again, the example is take the congruence lattice of a group and the lattice of normal subgroups, or the congruence lattice of a commutative ring with units and the lattice of ideals of the ring, okay? They are isomorphic. And here is no different. Now, what are the normal elements? What are the normal elements? I mean, you know that in a commutative group, every subgroup is normal, right? And here is not so different, actually. I mean, but the point is that we want to describe the situation in which every filter is a congruence filter, okay? And how do we do it? Well, we use, there is a very nice trick developed by Gibson and Xenakis 20 years ago, and we can use these two derived operations. These are two derived unary operations, and we call them the left and right conjugates, okay, of X with respect to A. And then actually we can prove that you don't need to ask, I mean, you need, okay, we describe filters using closure properties, right? They are closed under multiplications, they are closed upwards, and they are closed underneath. But they are congruence filters if and only if they're also closed under these two derived operations, of course, for every possible choice of A, right? So this is a nice way of describing, and not surprisingly, it gives you a very nice description of congruence filters in general, right? So what is the congruence filter generated by a subset of a residuated lattice? Well, what do we have to do? We have to simply iterate these constructions, right? We have to iterate these two operations a sufficient number of times until we get inside. So let's denote by gamma n of A the set of iterated conjugates in A of length n. What does it mean? Well, it's a composition of n of these guys, either left or right conjugates, right? And using this, I can describe the filter generated by a subset in a residuated lattice. And you see the description is very, very, very similar to the one you would expect in a lattice, right? Because in a lattice, what do you have? Well, instead of gamma 1, gamma 1, A1, gamma n, AN, you would have A1, meet A2, meet AN, less or equal to B. Right? Now, of course, we cannot hope to, in general, to have such a simple expression, but we still can construct things, using these iterated conjugates. And though they seem complex to deal with, actually, after a while, you get the gist of it, and you're able to manipulate them in a very interesting manner. And you will see something of it in Sarah Zugolini's talk. We have special equations. I mean, what do we mean by special equations? Well, the lattice is integral if it satisfies the equation x less or equal to 1, which means that 1 is the uppermost element in the ordering, and it is commutative if the multiplication is commutative, and it is divisible if the ordering of A is the inverse divisibility ordering. Now, these three properties turn out to be very, very, very important. And again, you'll see something about them in the sequel. The first two properties are clearly described by equation. It is nice to see that also the third, that is not, equational at first sight, it's also been defined by two equations, these two ones, right? I mean, this is just an algebraic trick, nothing really important. Okay, I have to remember which time I have to stop. Okay, so I still have plenty of time. Fine. Now, okay, let's not talk about this. I've already observed that, right? In case of commutativity, there is, of course, only one residuation, right? Because, I mean, the way that the two slashes are defined, if the multiplication is commutative, well, they define exactly the same thing. So they are the same. And we can denote them by the classical symbol of the arrow, right? Now, it is clear that every commutative residuated lattice is normal. Why? Well, because you see, we have this. We have this that, actually normality can be somehow defined by equations. By that, I do not mean that the class of normal residuated lattices is definable by equation. That is not true, of course. I simply mean that if I have a variety of normal residuated lattices, then it must satisfy certain equations, which is a slightly different way of putting things, okay? I'm not going to go into this because I would have to fill too many details. But still, we can sort of believe that commutative residuated lattices are normal. So really, every filter is a congruence filter, and now we can treat congruences as filters, and filters are very, very nice objects to deal with, right? Okay. However, you will see in Sarah's talk that you can use iterated conjugates to mimic a lot of the properties of commutative residuated lattices. We can extend a lot of results to non-commutative residuated lattices, okay? Now, what is an FL algebra? An FL algebra is just a residuated lattice with an extra constant in the language. Note that we make no provision at all for the position of 0 in the ordering, right? We are not saying that 0 is less than 1. We are not saying that 0 and 1 have to be comparable. In fact, it may as well be possible that 1 is less than 0, or that the two elements are incomparable. This might seem strange, but really you have to understand that 1 and 0 here, they are, how can I say, a multi-purpose symbols, okay? So we use 1 for truth and 0 for falsity. And so you might conceive a logic in which the set, all the things that are above 1 are true, all the things that are below 0 are false. But of course, there are things that can be below 0 and above 1. And well, this is a phenomenon known as paraconsistency, right? And so, I mean, we can in this very general framework, we can take care also of the various, non-explosive logics that appear in the literature. Something that Carles hasn't talked about, but I mean, and I'm not going to talk about that too, but just mention that this is a very, very general setting. It can accommodate a lot of different things, and this is the real power of choosing this kind of setting. Okay. Now, of course, FL algebras are in particular residuated lattices, right? And so everything we said about residuated lattices holds for FL algebras as well. The only difference is that we have null operation in the type. So what really changes? What does it change really? Well, homomorphic images are the same, right? Because congruences are the same. A constant is not going to alter the congruent structure. Direct products, well, more or less they are the same. So where is the real change? Subalgebras. Subalgebras change because, I mean, a subalgebra of an L algebra must contain 0, while a subalgebra of a residuated lattice must not contain the bottom element if there is one, right? So the situation actually changes, and I mean, it's very interesting to understand what really changes, but this belongs more to algebra than to logic, so I'll skip it. But we will apply the process of algebraization to the variety of commutative FL algebras, and these are commonly denoted by FLE because E stands for exchange, right? So they are going to be the algebraic semantics of the logic that Carles has called SLAE. Okay. Now, let's start defining a logic starting from the algebra. What is the assertional logic of a subvariety of FLE algebras? Well, as usual, logic is a set of things with some consequence operator. So I'm not going to be very precise here. But I mean, what is the language? The language consists of the operations, right? So that we see as connectives. So join, meet, multiplication, and arrow. Remember, it's a commutative case, so only one arrow. Okay. And the two truth constants, 0 and 1. I want to consider 0 the falsum and 1 the verum, the truth. Okay. So the symbols are interpreted in any algebra as the corresponding operations. And so the formulas of the logic are just a term of the free algebra over countably many generators in K, right? So I mean, it's just a very, very natural algebraic interpretations. And what is the logical rule? The logical rule is modus ponens, of course. This is the only logical rule. And the logical consequence is defined in the following way. A set of sentences proves phi if for any A in the class K, well, we have to mention the class K, right? Because this is the logic of K, the assertional logic of K. And for any homomorphism from the set of formulas in LK to A, we have this. I mean, this implication holds, right? And this tells you basically that if H of gamma is true for all gamma in gamma, then H of phi is true, okay? Because you see, H gamma mit 1 equals 1 means that H gamma is greater than 1, and greater than 1 is in the back of our head, true, right? Okay, so this is certainly a logic, and it is a quickly implicative logic in the sense of Carles, and we can connect this logic with another consequence relation characteristic of the class of algebras, which I call the semantical consequence relation. Okay, actually, this is just what we study in basic algebra classes, right? I mean, if I have a set of equations and epsilon is an equation, then epsilon is a semantical consequence of gamma if for all algebras in K, if A is a model of gamma, which intuitively means that if I plug in the elements of A in the variables of gamma, then I get something which holds, okay? Then A is a model of epsilon. Forgive me if I am a little bit, imprecise in saying these things, but I mean, this is just, this is the usual semantical consequence in model theory, so nothing really major about it. But the nice thing is that the semantical consequence relation and the assertional logic, well, they have interesting properties. And there is a very strict relation between them. So what are the properties? These are the properties, right? So we have this sort of, modified push and pop. Let's use Carles terminology. And well, we have this, right? This tells you that, if it is true that, okay, delta is equal to gamma, if it is true that delta is greater than gamma and gamma is greater than delta, right? Or if you prefer, if it's true that delta implies gamma is true and gamma implies delta is true, okay? And also, of course, the opposite. So this is an if and only if. But these are the two interesting things. I mean, we can write the logical, the assertional logic consequence and the semantical consequence. We can write them one in terms of the other. So a set of formulas, okay? And in this case, what are the formulas? I mean, they are the equations of the language, right? Because we are in LK. This is the assertional logic. So this is true if and only if every time that something here is true, so Phi-MIT1 is equal to 1, then, oh, this is wrong. I mean, I should have used a different symbol here, right? Because I mean, I'm using, or here better. So this means that gamma, phi is a consequence of gamma if the class psi mit1 equals 1 for psi and gamma semantically implies phi mit1 equals 1. And vice versa. So sigma semantically implies delta equals gamma if and only if this set of sentences, of formulas, okay, implies gamma if and only if delta in the assertional logic. Now, here I'm willingly confusing the algebraic terminology and the logical terminology. And I'm doing it on purpose because I mean, I just want to show you that this is a very, very natural interpretation of the implication with respect to the idea of ordering and the idea of, semantical consequence. Now, these two things are very, very important. These two relations are noteworthy, and this will constitute the template for our definition of equivalent algebraic semantics. Because remember, this is our purpose, right? We start from a logic. We want to describe what is its equivalent algebraic semantics. So let's take the full Lambert calculus with the full exchange action, okay, for one of the implications. So this is another way of saying SLAE, okay? As I told you several times, in this case, the distributed connective that Carles described as commercial E is commutative. And so we have one implication. Now, take a schematic extension of this logic. Well, we can associate to this schematic extension a class of algebras in the following way. Okay, these algebras will be algebras in FL of A, FLE. Okay, and the operation on the algebras correspond to the logical connectives denoted by the same symbols. So the join is the logical disjunction, the mit is the logical conjunction, and the arrow is the implication, and the multiplication is just the commercially connective that Carles described, okay? And when does an algebra belong to this class? Well, An algebra belongs to this class if and only if for any homomorphism H from the set of formulas in the language L to A, and for any set of formulas in L, this implication holds. And this is exactly, it looks like the same as before, right? So we are apparently saying the same thing twice. Really we are, but in a sense we are not, because before we were talking about a specific logic, the assertional logic of a class of algebras. Here we are talking about any logic extending, you know, the full Albert calculus with exchange, okay? Now, when is the logic algebraizable? So we start from a schematic extension, we define this class of algebras. Well, a logic is algebraizable if and only if the logical consequence in L and the semantical consequence in K are related exactly as the logical consequence in the assertional logic and the semantical consequence. In other words, it is just this definition here, where instead of LK, I have L. Okay, so the definition of assertional logic is the template for our equivalent algebraic semantics. And of course, I mean, one can say that the assertional logic of any variety of FL algebras is algebraizable, and its equivalent algebraic semantics is the variety itself, right? So the assertional logic is just one of those logics whose equivalent algebraic semantics is the class K, okay? Now, in general, we can prove that this is, I mean, of course, this is a very specific instance of the definition of algebraizability. It's the definition tailored over the concept of residuated lattice, commutative residuated lattice indeed, okay? But we can give a much more general definition, and maybe you'll see something like this in Tommaso Moraschini's talk, but I mean, but this is only a very particular instance, okay? In general, we can prove that if there is something that we can call an equivalent algebraic semantics of a logic, then it's always a quasi-variety of algebras. Well, probably my logicians friends will correct me and will say, okay, only if the logic is proto-algebraic, right? But I mean, it's that would be, you know, to go too much into details. I don't like to do that. But still, in this case, we can actually prove that every schematic extension of the logic I considered is algebraizable, or as they say, strongly algebraizable. And its equivalent algebraic semantics is the subvariety axiomatized by these equations. So you see, here I take a set of, you know, this is the extension, right? I have new actions. These actions are written using connectives, and the connectives are the operations of the algebras. So I can think to them as, you know, just terms of the algebra, of the free algebra over countably many generators. So this makes perfect sense, right? This is epsilon I mit 1 equals 1 is just an equation in the language of the equivalent algebraic semantics. And so this is just a set of actions. This is just a set of actions for the class K that can be obtained by the schematic extension of SLE. Okay. In other words, there is a total correspondence between the lattice of subvarieties of FLE and the lattice of logic extending this logic. I mean, it's a dual lattice isomorphism, of course, because, you know, subvarieties go down and extensions go up. So this is always something that as an algebraist, I tend to see, you know, inclusions, and most logicians see these things as extensions. So we always get the things upside down. And but still, basically, we can switch back and forth from a logic to its algebraic semantics in a very, very effective way. And well, what do I mean by effective? I mean, you can translate concepts from one setting to the other. And there is a huge list of examples, right? I mean, I'm not going to give you any specific example. Again, you will see something in the next talks. But still, this is a very effective machinery, right? You take an algebraic concept, you can translate this into a logical concept. You take a logical concept, you can look at what it means algebraically. And in the literature, there are dozens of examples of this kind of argument. Now, of course, we have seen only a very special case of algebraization, right? There is a very general definition in the block-Picozzi style. And of course, I mean, it is at the expense of complicating things a lot, a lot, okay? But, you know, the fact that the equivalent algebraic semantics of this very specific minimal lot, because I mean, I use the commutative case, but the same argument can be carried out in the non-commutative case as long as we have associativity. And of course, it can be carried out also without associativity, but you get a class that is very hard to deal with. I mean, non-associative multiplication is not very easy, even though there are some interesting results. I mean, I can mention a paper by Nick Galatos on frames for this, you know, relational semantics for this kind of stuff. Very deep and very dense paper. Okay, but you see, we have a very good reason to investigate residuated lattices from an algebraic point of view. We already had very good reasons to do that, right? But now we have one more. Now we have one more. And let me mention that the real connection between these two things happened in a conference in Barcelona in 1996. I was at that conference, and everybody was there. Everybody in algebraic logic was there, and in particular, Isabel Ferrerin was there, and we sort of realized that, you know, the structures that people in Spain were like Godó and Esteva and, you know, and other people in Spain were studying were in fact hoops. That is a particular, you know, algebraic structure that had been introduced way before for totally different reasons, right? And then the connection between these two fields was made, and from then on, I mean, things blossomed. You know, I mean, there are hundreds of papers on the subject. Maybe too many, but still, this is a very good reason to investigate residuated lattice from an algebraic point of view, and this is what I've been doing in the last part of my career, right? Now, of course, I mean, the monoidal part is the real novelty, right? I mean, if you consider only the lattice structure, well, but the monoidal part, and more than that, I mean, the monoidal residuated part is that what gives you the most interesting connections. And I mean, as a matter of fact, after the break, you'll see some of these connections in Nick Galatos' talk. Thank you very much.
Okay.
Okay, now we have a break until 4:20. Okay, so we have 8 minutes break. Okay, I think that we can resume the session. And well, let me introduce Nick Galathos. Nick Galathos is a full professor at the University of Denver, and I have to thank him twice because I mean, I know he has a lesson, he has to give a lecture at 5, I think, and he'll have only 5 minutes to get to the class after he's finished talking. So I hope he'll be on time. So Nick, you can start.
Thank you, Paolo. So I'm going to talk about lattice ordered groups and monoids. So these should be probably topics that are more related to the audience here about semi-groups. The addition is that we also consider ordered structures. So this is joint work with Almudena Colasito, George Metcalf, and Simon Sanchi. So let me start by saying a few things about the outline. I will mainly give a background on lattice ordered groups, or L groups as they're known, and focus on their redux where we remove the inverse. And I'm going to talk about why we want to do that and what are the benefits. The resulting structures are going to be monoids. They're not going to have inverses, but they're going to contain the lattice structures. They're going to be lattice ordered monoids, and the lattice is actually going to end up being distributive. So we're going to be calling them DLMs, or distributive lattice ordered monoids. I think that's all I'm going to have time to do. In the end, maybe I'll just flash a few slides about the case of the totally ordered, the variety generated by the totally ordered ones, the axiomatization, a few remarks about syntactic systems relating to what Carles and Paulos mentioned, and then some maybe what I think are new results about free groups and free monoids and the orderability of these structures. So let me start with the definition of a lattice ordered group, which is just a group and a lattice on the same structure, and lattice has infima and suprema. There's an underlying order here, and we assume minimal compatibility between the two, namely that the multiplication of the group is compatible with the order given by the lattice. What do we mean compatible? You can say it in 3 different ways, which are end up all being equivalent in the presence of having a group, namely that the multiplication is preserves the order, or that it distributes over the joints, or that it distributes over the meat. And the last 2, for example, can be written equationally. So this whole class is defined by equations. It's an equationally defined class of algebras, therefore it's a variety. And we denote it by LG. Now, examples, we know them from numbers. You can take the integers with the usual order, the minimum and the maximum being the supremum and the infimum, the usual addition and subtraction. This is a group, this is a lattice, and addition is order preserving. The reals, the complex numbers, either lexicographically or coordinate-wise, give you examples. All of these are commutative. If you want to go to non-commutative examples, you have to do the same thing you do for groups. You go to permutation, symmetric groups. So the difference here is that if you take symmetric groups, you don't get an order. That's why we start not with a set C, but with a totally ordered set C, a set that has a total order, it's a chain. And we, instead of taking just permutations, we take only those permutations that preserve the order via these functions. Or if you want to see it differently, they're automorphisms of this ordered structure, the chain with the order. So you can start with any chain you want, but if you take a finite chain and or even the naturals, this will give you a 1 element example. If you take the integers, you only get the translation by a fixed integer. So this gives you the integers as a group, as an L group. It gets interesting when you go to the chain of the real numbers and you take order permutations of those, and this is a very rich structure, it's not commutative. One of the reasons I'm interested in these structures is because they're special cases of what Paolo called the residuative lattices, but you don't know anything, need to know anything more, just know what a group is and what a lattice is for this talk. So the celebrated Holland's embedding theorem is an analog of Cayley's theorem, which says that every lattice order group can be embedded into the order permutations of some chain. It's not as cheap as Cayley's theorem. In Cayley's theorem, you take the group you want to represent, and you take as the underlying set of the group, on which you do the left regular representation with left multiplication. But here you cannot just take the L group, forget about the multiplication and look at the order, because the order might be a lattice order you want to chain. So there's a little bit of work to just get a chain out of this and then take the left regular representation. You can easily prove, even though it's not stipulated here in the first condition, that the lattice, because you have a group and the compatibility, you can actually prove that the lattice in this case has to be distributive. So these lattices are special in that sense. And also you have the usual laws that the negation converts joins to meets and meets to joins, the usual De Morgan laws. So that's where the logic essentially you can think of the inversion here, logically speaking, as a negation of sorts. So in the abelian case, things are very, very simple. The variety of abelian L groups is actually generated by the first example I gave you, by the integers with the usual ordering. That's a result by Weinberg. And therefore, if I give you an equation in abelian L groups and you want to decide if it's true or not, you just need to check it in the integers. And for that, you can use linear programming algorithms. So that's a decidable problem. An intermediate situation, not going all the way to all L groups, is those that are called representable L groups or semi-linear. These are the ones, the variety generated by just the totally ordered ones. And there are totally ordered that are not abelian, so you get a bigger variety. So this variety is axiomatized, for example, by this equation here. And I'm going to come back to that towards the end of my talk. But we still don't know anything about the decidability of the equational theory. We cannot get a handle on this yet. The whole variety is also kind of understood in some sense, has been studied extensively, but this is the content of Holland's generation theorem that says that the variety of L groups is generated by a single very nice algebra. It's the algebra we saw of all of the order permutations of the real line. Also, if you want, you can take Q, the rationals. So if you want to decide an equation in all L groups in the variety, it's just enough to know if it holds in the order permutations of the reals or the rationals. And Holland and McCleary built on that, and they prove that actually you can do that. They provide an algorithm that decides if an equation is valid in this one, and actually has been implemented online by Peter Gibson. So the algorithm, what it does, if you type in an equation, if it fails, it will actually give you a counterexample. In what sense? Counterexamples are infinite in this setting because the functions from reals to reals are infinitary objects, but it will give you finitely many points, and then you can extend it linearly. So it's easy to recover an actual counterexample, but it gives you a finitary description, what is called a diagram. If the equation is true, it won't give you a counterexample. It will go through all of the necessarily finite, they prove, are needed checks for diagrams, and this will be a determination that it's a true equation. But it will not give you an actual proof of it in equational logic. So I'm going to come back to this point in the next slide. I want to just mention that if you want to decide equations, because multiplication distributes over joins and meets, and because inversion, taking the inverse also switches meets and joins, it can be pushed down. And because you have inverses, you can move everything to one side by multiplying by the inverse. So in the end, you only need to decide equations of the form 1 is less or equal to a join of group terms, or the meet of group terms is less or equal to 1, depending on which side you move the inverse. So let me say a few things about systems, decision systems, derivation systems for lattice order groups. Usually, in equational logic, we have this rule of transitivity. But this is a little bit problematic if you want to analyze proofs backwards. If you have a proof in equational logic and the last step was transitivity, then if you're given the equation that you want to decide if it's true or not, you don't know if there is a proof. You have to consider that the last step was transitivity, and then you have to guess what the B is, and there could be infinitely many choices for the term B here. So this is not amenable to a proof theoretic analysis. But with George, back in 2016, we give a derivation system for L groups that avoids having the transitivity rule. Actually, it avoids having any rule where there are unexpected terms like that, like B, appearing in the proof. The system is analytic in that sense. Also, we give a different system where the transitivity rule is permitted, the terms B are not wild, they're restricted to a finite set already given and deducible from the equation that you're given. The last system actually is inspired by Holland's and McCleary's discernibility result. And we use that to prove a syntactic version of it, but gives us more handle because we do it in a careful way. And we actually can determine the complexity to be co-NP complete of the equational theory of L groups. Also, we fixed that issue that we mentioned. If the equation is true, we don't get a derivation. Here we can actually get a derivation in standard equational logic, or if you want, in the system that Carles mentioned, which is the full Lambda calculus, a hypersequent actually calculus for that. As a byproduct, we provide an independent proof of Holland's generation theorem that the variety is generated by the automorphisms of the reals without having to use the heavy machinery of Holland's embedding theorem, the Cayley-like theorem that I mentioned, where you have to worry about what chain to have and so on. So what's missing, what was missing and gave partly the motivation for the talk I'm giving now, is that these systems, although very nice and they succeed in providing desirability or analyticity, they still don't have nice residuated frames. They don't have the other leg of the three-legged stool that was mentioned essentially in Carles and Paulo's talk, that you have the syntactic aspects, the algebraic aspects, but also the relational theoretic aspects. You don't have the relational theory for this. And residual lattices tap into this when you have a nice derivation system. These are ad hoc. So this is because the L group axiom, the group axiom actually itself, the position of the inverse makes it complicated and puts it very high up in some hierarchy of difficulty of axiomatizations, and we cannot access it. So one way to deal with it is to just remove the inverse altogether. Remove the inversion as a fundamental operation in lattice order groups, you get poorer structures. So of course, the obvious thing to worry about is that maybe you lose a lot of the information, you lose a lot of the things that you can do with them. We will prove that you lose nothing. So that's the motivation here, and that's a surprising aspect. So let me delve into removing the inverse. So we're gonna take, you take an L group, you remove the inverse as an operation, you keep the same L group, but you think of the other operations only, the lattice and the monoid operations. And you also, maybe if you want, take subalgebras of that, and then those will not support an inverse anymore. So these will still though be lattices. They will be distributive lattices, and multiplication will distribute over join and meet. So there will be lattice order monoids that are distributive in these senses, and we call them distributive L monoids. And they form a variety because I just gave you the axiomatization. So definitely one process gives you distributive L monoids, but maybe there is something more special about these inverse free subreducts of L groups. Maybe there are other equations that we're missing except for these obvious distributivity ones. And there's bad news in the next pause, but first some examples of these. Instead of taking order permutations on a chain, you can just take arbitrary order preserving functions from a chain to another chain. And these are the prototypical examples of these. So the bad news comes from Repnitsky that shows that at least in the abelian case, there is a disconnect here. If you take the inverse free redux of abelian L groups, not only are they commutative DLMs, but they satisfy extra equations. And if you put an extra equation, you're still missing an equation, and you can never axiomatize it with finitely many equations. It's non-finitely based. So you're missing a lot. There's a huge discrepancy between the obvious equations you get that you can write down and what's actually axiomatizing explicitly the inverse free subreducts. So it's a huge surprise, because it's a huge surprise to us even that the pathology doesn't appear in the general case of the whole variety of L groups. For L groups, these are precisely the equations that you need to characterize the inverse free subreducts, these obvious distributivity properties. So I want to spend a little bit of time, and I think I'm going to have time today to give a little bit of the idea of the proof. So equivalently, you can say that the interesting direction of this is that if you have an inverse free equation, because we're talking about inverse free redux, that fails in distributive lattice order monoids, it necessarily fails in some lattice order group. It doesn't fail in some arbitrary DLM. It fails in a DLM that comes actually from an L group. So I'm gonna split this into this interesting interaction into two steps. One is by showing first that the variety I'm talking about, these examples here are not just examples. Even if the chain is finite, they give you everything. So as a variety, these DLMs are generated exactly by the endomorphisms, the order preserving functions on a finite chain. So this gets us a little bit in the direction we need. If you have an inverse-free equation that fails in DLM, doesn't yet fail in an L group, but at least it fails in one of these guys where C is finite. And that's very easy to do, actually, this lemma, it's very easy to prove, because we use the analog of Cayley's theorem for DLMs that was actually already known in the literature by Tsinakis and Pauli, and before that by Anderson and Edwards, which says that if you have an equation that fails in a DLM, it actually fails in one of these symmetric ones, if you want. But the chain doesn't have to be finite. So how do we get a finite chain? Very easily. If the equation fails in one of these guys, what does it mean it fails in one of these guys? If you replace the variables by actual elements of the algebra, which are functions, so if there are specific functions in the algebra, so that if you plug them into the equation, you get different results, different elements of the algebra, different functions, because the algebra has functions on C. So when do functions differ? They differ if they differ at least in the value of at least one point of C. So there is at least one point of C where these two functions, if you apply them to P, they differ. And here I'm using the standard notation of for automorphisms and endomorphisms, this function is applied to its argument by writing the function on the right of the argument. So how do you get the finite chain now? Well, you just take only the element P and this element and that element and all of the elements that you have to look at when you're actually evaluating this term and all of its subterms. And then what you get is by restricting to a finite chain, and the functions now only restrict them to this part of the chain. They're not going to be fully defined because the images sometimes step out of the finite subchain C prime. Nevertheless, just keep them undefined, keep them as partial maps. How do we extend them to total maps? It's okay if you have a partial map, then just define it in any way you want on the undefined points, as long as you don't violate order preservation. You have some maybe point below, point above that goes specifically, just send it somewhere in between those points or to the same point. It's okay if you collapse points anyways. We're not interested. Even the original evaluation, the endomorphisms could be very far away from being one-to-one. So that's how you prove this, but it's not big help because we really want to get to an L group, and we really want one-to-one maps, because in L groups you have order permutations, injections. So how do we do that? So this is the next step now from this failure on an endomorphism of C for a finite chain. I want to fail in a specific L group, and the L group is actually the generating L group. It's the endomorphisms of R or of Q. How do we get a failure in there? So here's the starting point. We have the failure, we have this finite chain, we have these explicit points where it fails. The idea is the following now. From this finite chain in these highly non-injective functions, I want to get injections. I want, even though partial. So there's not enough space, so I'm going to enlarge this chain C to a bigger chain C bar, but still finite, where I remedy this failure of injectivity. How do I do that? I duplicate points. If you are in a situation where the function f takes 2 points, P1 and P, 2 different points to the same point, I'll just duplicate that point Q to a Q1 and Q2, and I'll set P1 to Q1 and P2 to Q2, and then the function will be injective at that point. Well, that's a little bit naive, because the point you duplicated could be the input of yet another function, let's say G. You may have a function G that takes that point q to some other point, and by duplicating the points, you have made the function g non-injective now, because the q1 and the q2 will be sent by g to something else. And then these functions f and g might be one of these f1 up to fn, and then you keep doing that, and then because you have no control how these functions appear in the equation, you may end up going around and changing your tail. So how do we do that in a consistent way so that the failure still remains? I'm gonna talk about in an example on the next slide. But once you do that, you're home free, because now you have partially injective bijections on a finite chain. And then how do you get them into total injections? You cannot on the chain, but you can see this chain C bar sitting inside Q. Q is a big dense chain, and you can also throw in elements, and you can see any finite chain inside Q. Because well, it's omega categorical, and then you just have enough space inside Q to remedy that to total projection. So, but the interesting point is this: I'm going to show with an example how to get from how do you reestablish the injectivity. So here I took the smallest possible example. I took the smallest possible non-trivial chain 0, 1, and I took the endomorphisms on this two-element chain. There are only 3 endomorphisms because order preserving endomorphisms, because you can either take the constant 0 or the constant 1 or the identity function. The one that switches, that function is not allowed because it's order reversing. So which equation am I thinking about that fails into this one? For the example, I took this equation, yxy is less or equal to xyx. And I'll show you why it fails in this one. I'll give you specific evaluation from the free two-generated distributive L monoid into this one. You simply assign to the variable x the constant 0. 0 goes to 0, 0 goes to 1 goes to 0. The constant 0 function, you can also see it here. This is the 0, 1, both of them go to 0. That's how you evaluate the variable x. You evaluate the variable y by a different automorphism, the constant 1 automorphism. And here's why this equation fails. It fails because phi yxy and phi xyx are different functions because they differ at the point 1, to be specific. What does this function do to the point 1? Well, this is a homomorphism, so it sends multiplication to composition of functions. So this is just the composition of the evaluations. So I just need to trace how 1 goes if I apply phi y, phi x, phi y. So here's the tracing of it. I start with 1, I apply phi y, it goes to 1. I apply phi x, it goes to 0. And I apply phi y, and it ends up being at 1, which is a different point than applying this composition phi x, phi y, phi x. It gives you a value 0 that's not greater or equal as it's supposed to be, so it witnesses the failure of the inequality. Okay, great. But it witnesses it by highly non-injective functions. These are constant even functions. How do we fix that? By making them injective on maybe a bigger chain, but still finite. The idea is to duplicate points. I have 2 points, 0 and 1. I'll create copies of 1, enough copies of 1, and enough copies of 0. Here's the resulting 7-element chain. These 4, think of them as copies of 1 because they finish in 1, and think of these as copies of 0 because they finish at 0. So how do we construct this 7-element chain from this 2-element chain? Well, instead of taking the points, you care about not just the point itself, but how you arrived at this point, what path you took to arrive at this point. So this chain consists of paths that end at the point 1 or at the point 0. Which paths? Only the ones that are needed for the failure, so just a handful of them. The path that starts and ends exactly where it starts, it's the subterm of this, that's the empty subterm. You start at 1, you stop at 1, you have a 1-element path. Another path is the y path. You start at 1 and you do a y step, a phi sub y step. That phi sub y step takes you from 1 to 1. So you have the path from 1, start at 1, finish at 1. You have the xy step. So you do a y and an x, sorry, yx. So that's why it's useful if you write the argument to the left, because it's a starting point. So 1, 1, 0, that's a path. Another path, YXY 1, 1, 0, 1, up to 4 length 4 and no more, and not even all 4 length paths, only the ones that come up from initial subterms of either the left-hand side or the right-hand side of the equation. This is the chain, and how do you order it? Well, the ones have to be bigger than the zeros. Then if there's a tie between the ones, how did you arrive at the 1? With the 1, it's bigger than arriving at 0. So it's reverse lexicographic from right to left, and the empty path before 1 is a 0, before 1 is the empty, so empty is smaller than 0, which is smaller than 1. So that's the usual lexicographic ordering, but for Hebrew or Arabic instead of English. So that's a chain. And now we have made it non-injective because here's the chain. How do I define these new functions y and x? Well, let's take this point. You want to see where to send it. It's a 1. Phi sub y sends 1 to 1, but which of the ones? Well, you take 1 and you just do a y step. So this takes you to 1, 1, which is here. 1, 1 is at this level. So you send 1 to 1, 1. Let's say you have this path, this element of the chain. If you do a y step, 0 goes to 1. So you put an extra 1 after it, 1, 1, 0, 1. And it's at this level. You put it there. How about this one? This step, if you do a y step, 0 goes to 1, so it would be 1, 0, 1, 0, 1. Well, that's not in our chain. Leave it undefined. Okay, leave it undefined, but at least you've made it injective. So, and now the failure is still there because by this, the left-hand side of the equation, the 1 goes to one of the ones, but under the other path, which I don't have this picture, with the xyx, it will end up in one of the zeros. So again, you exhibit the failure in there. So that's the idea. If you have a path, you want to apply the function, you just augment the path. It's a longer path by f if this f is defined and gives you a valid path, if the latter is a path. Now, once you do that, again, as I mentioned, you can view this finite chain inside Q. So here, where do you send this point? Where you visualize this in Q, these are elements of Q. Q is dense. There's a midpoint in there. Send this to the midpoint and extend this interval linearly to that interval, and likewise, and you have enough space, and you have the failure of the equation inside the automorphisms of Q, inside the lattice order group. So there's nothing special about distributive L monoids, equationally speaking, in terms of groups. So we were successful. The validity of inverse free equations in L groups can be reduced to their validity in simpler structures than L groups, distributive L monoids. But that's not what I promised in the beginning. We don't have only inverse free equations. We want to study the whole theory of L groups, including the inverses. What do we do about equations that do have inverses? That's something that the abelian case, at least, is easy, because in the abelian case, you can get rid of inverses. If you have an inverse appearing somewhere, just with commutativity, bring it to the front of the group term it belongs to, and then just multiply by G on the left. Multiplication by G is order preserving, and it distributes over meets, so it gets rid of the inverses. You can clear denominators in the abelian case. So there's a nice link in the abelian case, because in the abelian case, if you stay with L groups, you can massage equations that have inverses into equations that don't have inverses. The problem is that you cannot capitalize on this because of Repnitsky. Repnitsky proved that then, okay, you have an equation without inverses to check in abelian L groups, but that doesn't translate nicely to the same equation holding in the commutative DLMs. That's where the break appears in L groups. And now that's not the problem for us. We know from the previous slide that an inverse free equation, checking it in an L group or in DLM, it's okay. The problem is clearing the denominators, getting rid of the inverses while you still check in L groups. How do we get rid of inverses if they're trapped inside and we cannot move them? That's a difficult problem. And it was surprising that it actually is possible. If you have an inverse trapped in here, you can change that to this kind of identity. It has one more variable, but it's a small price to pay. And there is a way to get to this equation. So there is a way to get rid of inverses, to clear denominators in a highly non-obvious way. How did we come up with this way? The truth is that actually we came from syntactic proof theoretic ways. This is actually similar to the density rule, totally different subject of study. It's about equations failing in dense chains as opposed to non-dense chains, nothing to do with this L group stuff. But proof theoretically is very similar, and we could prove elimination of this rule. In the end, we prove this theorem without using any proof theory or anything. We have Holland's now theorem. Once we know what to do, you can check, you can link the two, because we're talking about validity in L groups. So yes, we can go all the way. So we can have an inverse including equation in L groups and go all the way to an inverse without inverses equation in the simpler structures of distributive L monoids. So, or repeated multiplications of this. So we only need to decide equations in these DLMs. So you have this hybrid system. You first reduce inverses and then you fit it into a system for distributive L monoids. Is there a system for distributive L monoids? Yes, there is. And that's the slides I'm going to go over very quickly now. There is a system. It has been developed by in collaboration with Peter Gibsons a few years back. It has all of the relational semantics, all of the frames, everything you want is there. So we have all of the nice proof theory through the back door by removing the inverses in a conservative way, and then recovering everything and studying L groups through this distributive L monoids. How about the intermediate case, not the abelian where it fails, not the whole variety where it holds, the semi-linear one, the ones that are generated by totally ordered non-abelian ones? Well, there, unfortunately, the discrepancy persists. We prove that it's not the whole variety. So we specifically come up with an equation about this. So the discrepancy there, we don't even know what this variety then is of semi-linear DLMs. We just know that algebraically speaking, it's generated by totally ordered ones. But we don't have an axiomatization even with this. We just know that the axiomatization is different than the one we want. And so we've at least fixed that. We come up with an axiomatization. This is an axiom here. It's just a single equation with 6 variables. Essentially tells you that you can exchange the place of the x and the y in some context. Here is a meet less or equal to a join. So we also understand very well the semi-linear case. We're still conjecture that is also non-finitely based, and we're after finding some axiomatizations. This is the equation for representable L groups, and it's a consequence of this one. It's a sanity check. And finally, the last slide is that this allows us to do something very different, to consider now the free group and the free monoid and look at total orders on them that are compatible on one side. These are called right orders, and they have been studied extensively. And for example, I just mentioned the corollary here that if you have a right order, total order on the free monoid, we can prove that it extends to right order on the free group, which as far as we know, it's a new result on the theory of free groups and free monoids. Thank you for your attention.
Thanks, Nick, for this very, very deep and interesting talk. I mean, the next speaker is Sara Golini. Sara Golini, she is a researcher at the, well, I have to read it, at the Artificial Intelligence Research Institute in Barcelona. I believe it's located in the Universitat de Catalunya in Bejaterra, right? So, and she's going to talk about Halden completeness in residuated lattices. This talk is going to be a little bit more logical than the totally algebraic talk we have heard from Nick. So, Sarah, you may go.
Okay, thank you. I hope you can all hear me all right. Yes. Okay, good. Thank you very much for the introduction, and thank you for inviting me to speak in this occasion. And of course, thank you all to the organizers for organizing this conference. Maybe one day we will all meet in person, which would be even nicer. Today I will be talking about how the logical property of Halden completeness plays out algebraically in residuated lattices. And the new results that I will be presenting today are part of a joint work with Paolo. So the background of all this special session is algebraic logic, right? So this is going to be the background of this talk as well. And actually, really the aim of my talk is to give you an example, a manifestation of this interesting and beautiful, say, connection between algebra and logic. And in particular, this connection is going to happen in residuated lattices, so the structures that have been presented to you early on. So we know that they are the equivalent algebraic semantics of substructural logics. Just to set up some notation, if I call a logic L, I will write V of L for its algebraic semantics. And if I write V for a variety, I will write L of V for its corresponding logic. So as I mentioned from the title, what I will show you now is how the purely logical property of being Halden complete, which I'm going to tell you exactly what it means, can be characterized by really algebraic properties of the corresponding algebraic semantics in this context. So what is Halden completeness? Well, Halden completeness is a weaker form of the disjunction property. So very easy to formulate the disjunction property in a substructural logic L. A logic has the disjunction property if whenever you have formula, let's say phi m psi, whenever their join is a theorem of the logic, which I will write it like this in symbols. So whenever this join of phi m psi is a theorem of a logic L, then either phi or psi are theorems. Now, of course, this is, for example, not a theorem. Does not hold in classical logic, right? Because, for example, in classical logic, the excluded middle law holds, right? So for any formula phi, you have that phi or not phi, this is a theorem, right? But of course, this doesn't mean that either phi or not psi are provable in classical logic. Of course, this holds instead for intuitionistic logic. But now, if we go a little further and we ask for this pair of formulas not to have any variables in common, then here we have what is called Halden completeness. So a logic L is Halden complete if it has the disjunction property, but with respect to any pair of formulas that have no variables in common. So now classical logic is Halden complete, but does not have the disjunction property. So these two properties are distinct. And as I said, I want to be telling you, I want to tell you about how this plays out in residuated lattices and what happens there if you try to study this property. So residual lattices, we have seen this notation before, but just to remind you again, we have a lattice structure, we have a monoidal structure, and we have this residuation property, right? Where essentially I really want you to think of these as division operations, right? To make sense of the residuation property algebraically. So I will be mentioning integral and commutative structures. Paolo mentioned them before, but just to remind you, I will call a residual lattice integral if the unit of the monoid is also the top element of the lattice. And of course, a residual lattice is commutative if the monoidal operation is commutative. And so, as Paolo was saying before, in this case, what happens is that the two divisions coincide. So x under y is equal to y over x. And usually this is going to be denoted by x arrow y. So here the connection of logic of the division with the implication of the logic is clearer. And I will be also mentioning bounded residual lattices or FL algebras as they were called before. These will be for me integral residual lattices where you also have the extra constant 0, right? That is the bottom element of the lattice. Examples of these, actually in particular example of bounded residual lattices, of course, are Boolean algebras and Ising algebras. Here you collapse essentially the monoidal operation and the meet of the lattice, right? And examples of residual lattices that are not necessarily bounded, actually they're not bounded, are lattice ordered groups that Nick was just talking about. Okay, so what happens to Halden completeness here? There is a beautiful theorem by Chiara and Ono that is about commutative and integral residual lattices and how you can characterize Halden completeness here. So if you take a variety V of commutative and integral residual lattices, then the following things are equivalent. So you have the logic associated to the variety V being Halden complete, if and only if these purely algebraic properties hold. So in particular, the logic is Halden complete if and only if the variety is joint reducible in the lattice of subvarieties of CRLLs. So, if anytime you take a variety, its subvarieties have a very natural lattice structure, right? You just take the intersection for the meet and the variety generated by the union of the class of algebras for the join. And so here we're saying that this logical property corresponds to the variety being joint reducible in this lattice. And these also correspond to a algebraic property of the generating algebra. So L of V is Halden complete if and only if V is actually generated by one algebra that is well connected. What is a well connected algebra? Well, so if you take an integral residual lattice, we'll be saying that this is well connected if one is joint irreducible. So if one is the joint of example, for example, so you have if X join Y is one, then either X is one or Y is one, right? Sorry. So this concept actually was introduced by Maximova to characterize the disjunction property in intermediate logic. So the rest of the talk is really going to be about how far can we go from here? Can we generalize this really nice result by Chiara and Ono? Can these be formulated more general? Because here we are asking these very strong properties of being commutative and integral. Can we say something if we don't have them? So the key ideas behind what they prove are really nice properties of commutative integral residual lattices, in particular, the fact that every subdirected reducible algebra in a variety that is integral and commutative are well connected. So being well connected is really a property of subdirected reducible algebras, and this is a key fact used in their proofs. And also, and this is going to be even more important for what follows, the fact that it's very easy to axiomatize the join of subvarieties, the join of varieties, if you have commutativity and integrality. In particular, for example, say that you have W and Z that are subvarieties of V, and say that W is axiomatized by, say, some term P of variables x1, xn, say, equal to 1, and Z is going to be axiomatized by some term Q of different variables, say y1, ym, equal to 1, then actually the join of these two varieties relative to V is just axiomatized by P join Q equal to 1. Okay, so this is very easy. But this only really happens in this very special case. So when you don't have commutativity, or actually when you don't have normality, things get way more complicated. So if you remember normality from Paolo's talk, essentially the idea is that if you don't have normality, you have to use these conjugates, right, to talk about congruencies. And so this makes things way more complicated, but this is what I'm going to talk about in a moment. So as I'm saying, both these things don't happen in general in residual lattices, but I want to show you exactly how far we can go from Chiara and Ono's result, and how we can characterize a Halden-like property in residual lattices without the use of commutativity and integrality. So I'm going to use a few minutes to tell you about how you can axiomatize the join of varieties in general in residual lattices. This is interesting on its own, and also I'm going to be needing it to show you our result. So Nick Galatos in his PhD thesis actually shows how you can obtain an infinite equational basis for the join of varieties of residual lattices. Now, if you have an infinite basis, you cannot do a lot with it with respect to what I'm going to need, but what he also shows is that there are some cases that actually are large classes of structures in which this basis simplifies to a finite set of equations. And this is exactly where we want to land. Many interesting varieties are included here. For example, all normal varieties, again, so in particular, all commutative varieties of residual lattices will be of this kind. But also representable varieties. So varieties where the subdirectly reducible algebras are totally ordered. So they are generated by totally ordered algebras. And also, again, lattice ordered groups. So many of the interesting structures that we know will be included in these cases. So here, when all of this happens, we will be able to generalize Chiara-Nonnou's result. So let me tell you what happens when you want to axiomatize the join of varieties of residual lattices. Say we take V to be any variety of residual lattices and say that you have two inequalities of the kind P bigger than 1 or Q bigger than 1, let's take them such that they do not hold in V. And we consider W and Z as before being axiomatized by the corresponding equations. So P-MIT1 is 1 and Q-MIT1 is 1 respectively. So how can we axiomatize the join, the variety that is the join of W and Z in the subvariety lattice of the residual lattices? So the idea is that it's not enough to just take the join of these terms, but what we need to do is to consider all the possible joins of iterated conjugates of the terms P and Q. What do I mean? I mean that we need to take sets of formulas of this kind. It's going to be an inductive definition. So I'm going to define this B of n of xy to be the set of equations of this kind. So we're taking all possible joins of iterated conjugates of length n, right, of x and y. So this could be x conjugate on the left, on the right, on the left, as many times, whatever conjugate you want, but you're going to take n of those. So this is a typical equation in there. And so this is for each n, it's going to be a finite set. You can look at this as a finite set. But to axiomatize the join of W and Z, we need all of these sets. Okay, so the join of W and Z is going to be axiomatized with respect to V by this set of all these Bn P of Q, where P of Q are these one that were axiomatizing W and Z. So still technically complicated, but I hope you can sort of follow me. This is an infinite equational basis. If it's very interesting that we can obtain it, right? But it is infinite. But so when can we make it finite? Well, the idea is that we can make it finite when we're able to stop at some n, right? When we don't need to consider all the following infinite steps. So when can we do that? Well, for example, we can do that when an algebra satisfies what we call the property G n plus 1, G by Galatos, because these are results that are essentially contained in his main proof, that is in his thesis. So we said that an algebra A satisfies the property G of n plus 1 if for all elements, for all pairs of elements A, B, and A, whenever A satisfies B of n of AB, so whenever all these joins, right, of iterated conjugates made on top of A and B are 1, then it also satisfies B of n plus 1. Let me write it down for you. It's not really needed that you understand it completely, but just to give you the gist, the idea is that if all these equations hold, if all these joins are 1 for all conjugates of length n, then also all these equations constructed with conjugates of length n plus 1 hold. So what does this mean? It means that you can stop at the step n because all the following step will be implied, right? And so if V satisfies, so if of course, I mean that V satisfies G of n plus 1 if all of its algebras satisfy it. And so in this case, if this is satisfied, then the join is going to be axiomatized by just these finite set of equations. Good. Example of these are the varieties that I've mentioned already to you. So we have all normal varieties, we have all representable varieties because they satisfy actually G of 0, 1. So you actually stop very early on. So these are easy to axiomatize. But for example, lattice order group are also an example of these happening, but they satisfy G of 1, 2. So you have to do one step of iteration more. But you still get finite axiomatizations whenever you have finally axiomatizable varieties. Good. So how can we use these to generalize Chiara-Nonno result? Because of course, Halden completeness was really playing with this join, right, of formulas, but now we have things that are more complicated. So we need to include these conjugates in our definition for this to make sense. So in our generalization, the generalization that we consider of Halden completeness, we're gonna hold it gamma of n completeness for all n in n. And I'm gonna be saying that a substructural logic L is gamma of n complete if for all formulas phi and psi that have no variables in common again, if all of these things here are theorems, these are the equivalent of the equations from before, right? So they are these joints of iterated conjugates of the formulas phi and psi. If all of these are theorems for the logic L, then it means that either phi was a theorem or psi was a theorem. It's clearly extending using these conjugates, right? This junction property we considered before of Halden completeness. So this is what happens from the logical side. What does it happen from the algebraic side? Well connectedness as well is gonna get more complicated in this more general situation. We're gonna say that a residual lattice A is gamma n connected if, again, you can probably even guess what's happening, but if for all A and B in the residual lattice, if whenever all of these equations hold, so if whenever all the joints of iterated conjugates of A and B are 1, then either A was actually above 1 or B was actually above 1. So you see, if you were to be in a commutative structure, then these conjugates are actually disappearing because these are all things that they will not matter anymore. And so you get exactly the notion of well-connectedness that we had before. So this is again a property really of the subdirected reducible algebras here. In fact, we can show that if you are in a variety of residual lattices that satisfy again these Galatos condition, right, of n plus 1. So the fact that you can stop at n and not look at conjugates of length bigger than n. So if you are in this situation, then every subdirected reducible algebra is gamma n connected. So this is really a property, a key property of subdirected reducible algebras here. And in this context, we can extend this result by Chiara-Nonno. So we can show that if you are in a variety V of residual lattices that satisfy Gn plus 1 for some n, then the logic corresponding to the variety is gamma n complete if and only if the variety V is jointly reducible in the subvariety lattice, if and only if V is generated by one single well-connected algebra. So of course, this is less logically meaningful than characterizing Halden completeness, right? But it is nonetheless very interesting because it does characterize joint reducibility in the subvariety lattice. And as Paolo said before in his introduction, as a consequence of algebraizability, the lattice of extensions of a substructural logic is dually isomorphic to the lattice of subvarieties of the corresponding variety. So studying the subvariety lattice is meaningful from the logical point of view, right? And so it's very important to understand the structure from one side and the other. And also, I would like to point out that if you take any variety V, its lattice of subvarieties is a dually algebraic lattice, which implies that every variety, so every element there, so every variety is the join of strictly jointly reducible elements. So the study of the strictly jointly reducible elements is interesting here to understand the subvariety lattice because they work as building blocks, let's say, of these lattice. So that's what I'm going to be talking about for the rest of the talk: joint reducible and strictly joint reducible elements in the subvariety lattice of residual lattices. And in particular, I'm going to answer two questions that were left open in the same paper by M.N.Hounkonnou about these structures. So let's see these two questions. First, let's see a very direct consequence of Birkhoff's theorem here. If you take any variety of algebras that is strictly joint reducible, then this is going to be generated by one single subdirected reducible algebra. Why? This is pretty easy to see, right? Because if you take the set of all subdirectly irreducible algebras in this variety, say a set of AIs, where each AI is subdirectly irreducible in V of A, then what happens? That if you take all of these varieties generated by the AIs and you take the join, right? Take the join of all of them, this is exactly V of A, right? Because this inclusion is obvious, right? The AIs were in the variety, so the variety generator and the variety, and so the join also needs to be included. But the other way around is also clear because A is generated by it's a subdirect product of the AIs, right? So the equality holds. So then we have seen that this V of A is a join, right, of varieties, but if it's strictly joint reducible, it has to be equal to one of them. So it's going to be generated by one single subdirectly reducible algebra. So it's a very natural question would be to ask whether the converse holds, right? So is it true that for every subdirectly reducible algebra generates a strictly joint irreducible variety? And we'll see later that this is really not true at all, even in very friendly varieties. Second question, what I've showed you in our more general context is that in varieties when one of these G of n conditions hold, then if you take a subdirectly reducible algebra, this has the property of being gamma n connected, which by the main theorem that I showed you, our generalization of M.N.Hounkonnou's result, this corresponds to saying that, that the variety generated by A is joint reducible. So here another natural question is, can we go back? So is it true that if a variety B is joint reducible in the subvariety lattice, then it's generated by a subdirectly reducible algebra? So actually these questions are really about what kind of varieties subdirectly reducible algebras generate. And we'll see that this second question will be answered positively in these varieties that we're studying. So let me see how much time do I have. I should be able to make it. So first thing, I'm going to show you that not all subdirectly reducible algebras generate strictly joint irreducible varieties. And this counterexample, we can find it in a very nice variety, the variety of basic hoops. These are integral and commutative structures. They are representable, so the subdirectly reducible ones are totally ordered. And they're also divisible. Divisibility is another property that Paolo showed before, but essentially you can express the meet operation as a combination, right, of the product and the implication. You don't really need more details right now. This is a very nice variety, and we know a lot about this structure because of this result by Alieno and Montagna, where they show that subdirectly reducible basic hoops are totally ordered. Well, this is because it's representable. Ordinal sums of Weisberg hoops. What am I saying? These Weisberg hoops are really nice algebras where you can also express the join, the other lattice operation using just the arrow. We know a lot about these. And you can use these Weisberg hoops, compose them with this operation of ordinal sums to obtain all totally ordered basic hoops. Just let me show you quickly what these ordinal sums are. Let's say that you have two totally ordered integral structures. Say you have A, you have this one here, and you have B with its one. You suppose that these top elements are actually the same, right? That they're constants in the language. Let's just think of them as being the same. I'll write them in black. Then how can you visualize the ordinal sum of A plus B? Well, essentially, you take B here and you copy on top of the rest of A without the top element 1. And then you really want to see these two pieces as subalgebras, right, with the operations inherited from before. And if you have an element X here and an element Y here, then XY is Y. And there is actually also X arrow Y. Now I have only one arrow because we're in commutative structures, but I could be doing this in non-commutative structures as well. So clearly this construction can be iterated. We're really just stacking these structures one on top of the other, right? And redefining the new operations as they meet. And another thing that Allione and Montagna prove, further than the characterization of these totally ordered basic groups, is that having up to n pieces in the ordinal sum is a property that can be characterized equationally. So if there is an equation that is satisfied by the totally ordered basic group if and only if its pieces, right, are in number up to n. So using these facts, we can show that if you take a subdirectly reducible basic group that instead has infinitely many components, right, infinitely many bubbles, right, in its ordinal sum decomposition, then the variety it generates is not strictly jointly reducible. Let me show you why, because it's a very short proof. So we're taking A to have infinitely many components, and let me hold C to be the set of all chains in the variety generated by A that have finite components. Now, of course, if you take one single chain with finitely many components, the variety it generates cannot be equal to the variety generated by A because of what I said here, right? Having up to n components is characterized by an equation. So this equation is going to satisfy in this variety here, but not in the variety generated by A. So these varieties are not the same for any of these chains. But if you take the join of all of these varieties, this is going to be exactly V of A, right? So and why is that? This is because if an equation fails in A, say an equation with n variables, right, x1, xn, then it's going to fail in the subalgebra of A generated by x1, xn. And from what I've showed you before about this ordinal sum construction, if your x1, let's say, is in one component, it's not going to generate elements from another component. And if you do products or implications, these are only the MIT. So you're not generating elements in other components, which means that essentially your equation is going to fill in an n-generated subalgebra that cannot have more than n components itself. So this holds. So the variety generated by A is a join of subvariety, and it's not equal to any one of them. So this is a failure of strictly joint reducibility. Okay, so let's go back to the other question. Is it true that if V is joint reducible, then it's generated by a single subdirected reducible algebra? Well, building on top of ideas that have been shown by respectively Aguzzoli and Bianchi and many authors, among which also Harless, we have been able to show the following theorem. So if you take a variety of residual lattices that satisfy this condition GNN plus 1 for some n, so right, you don't have to consider these conjugates of lengths bigger than n, then if V is joint reducible, then it is indeed generated by a subdirected reducible algebra. Let me just sketch you the proof. Here there's a lot of technical complication, but I just want to give you the idea. So if we start from a joint reducible variety that satisfies one of these conditions, then for the main theorem that I've showed you before, we know that this variety is generated by a gamma n connected algebra. Okay. Now, one can prove, actually using the Löwenheim's column theorem, that if you take this algebra A that is gamma n connected, then actually there exists a countable algebra that generates the same variety. This is because gamma n connectedness can be expressed as a first order formula, so we can find an algebra that generates essentially the same theory, elementary theory, so the same equational theory as well. So, okay, we have this variety V. Now we know that it's generated by a countable gamma-n connected algebra. Why is this relevant? Well, because then, and this is a lemma that is actually pretty complicated. If you're interested in the details, I will refer you to the paper we wrote with Paolo. I will give you the reference at the end. If you have a gamma-n connected algebra that I'm calling B now, then actually there exists a subdirected reducible algebra in the same variety in which you can embed the algebra B. And the key ideas here are that since this algebra is countable, we can actually write down a set of formulas that describe the operation table of the algebra B. Let's call it the diagram of B, the set of formulas. And also we can also write a formula that testifies, let's say, a failure of gamma-n connectedness. So essentially, B is going to be a counter model of this quasi-equation of the diagram of B and this, let's say, formula F that testifies the failure of gamma-n connectedness. Now, this means that in the variety generated by B, you're going to find a subdirectly reducible algebra that testifies this failure necessarily. And the trick is that you can embed then the algebra B in there because of the fact that it was satisfying this formula that constructs the operation table. Okay, anyway, the idea is that now, okay, we found what we wanted because clearly all these algebras are generating the same variety. And so if B is jointly reducible, then actually it's generated by a subdirected reducible algebra. And so what we showed is that if you have a variety of reciprocal lattices satisfying one of these conditions, G of n plus 1, for some n, then being joint reducible means being generated by a subdirected reducible algebra. So you see, this is a nice connection between these concepts. And this is one of the interesting things, right, about algebraic logic, that you can connect properties that seem different at first, but then they come together. Okay, so this is a general result, right? Actually, in the paper with Paolo, we show that if you have more information on how the subdirectly reducible algebras look like, you can be even more precise in characterizing these varieties that are jointly reducible. In particular, what we do is that we characterize the case of basic hoops. But anyway, just to recap, I told you everything I want to tell you about. So what I've showed you is that we can generalize Chiara-Nonno's characterization of Halden completeness in residual lattices, and in particular, we can characterize jointly reducible varieties. And we have seen that in large classes of structures, being jointly reducible corresponds to being generated by subdirected reducible algebra, but that being jointly reducible and strictly jointly reducible are distinct concepts, and in fact, subdirectly reducible algebras don't necessarily generate strictly jointly reducible varieties, even in very friendly cases. All these results are contained in this paper with Paolo that has been recently accepted for publication, but it's not so, and so it's not online yet, but you can check the preprint on the archive if you'd like. So thank you for listening. And
thanks, Sarah, for navigating us through this very, very complicated and technical paper. I mean, I was afraid it wasn't possible, but I mean, you did a very good job. I mean, actually, the paper is probably the most technical thing I've ever written in my life. I don't like calculations, you know, I'm a straight kind of guy. I mean, and just, if I see too many symbols, I get a headache. And anyway, now for the last talk of this colloquium, well, we have Tommaso Moraschini, and we are going to fly higher. Because I mean, you know, we mathematicians, we like to put things in boxes, right? We put things in boxes and then we look into the boxes and see what is inside. And then of course we have a huge bunch of boxes, right? And so we need a bigger box to collect all the boxes. And we start looking into this big box, and now the boxes are the object of our study. So we keep, you know, classifying things in this way. And so far you have seen what happens if we study, you know, classes of algebras or logics with certain properties. Now with Tommaso, you would see what happens if we consider the logics themselves as object of our study. So Tommaso Moraschini, he is from the Department of Philosophy of the University of Barcelona, and he's going to talk about the Leibniz hierarchy. Tommaso.
Thank you very much, Paolo. Hi, everyone. Before starting, let me just confirm that you can hear me well and see the slides. Is this okay? Wonderful. All right. Before beginning, let me thank the organizers for giving me the opportunity to talk in this workshop and in this special section with so many friends that I don't get to see in person since many times. So this talk will be about the Leibniz hierarchy, and I will tell you in a moment what this is. So let's start with some quick history, a recap. So in 1954, Maltsev discovered that a property of congruence lattices known as congruence permutability holds for the members of a variety K, if and only if in K a certain system of equations holds. What I mean by that, I mean that there exists a ternary term phi in variables x, y, z, such that in the variety K, it holds that phi of x, x, y is equal to y, and y is equal to phi of y, x, x. So again, the property of the shape of congruence lattices corresponds to the validity of a system of equations. Now, this was a breakthrough in universal algebra, and since then, many theorems like this have been discovered. For instance, in 1967, Johnson characterized congruence distributivity for varieties as the validity of a slightly more complex system of equations. And since then, the field flourished, and we had many theorems of this kind. So this observation prompted the conjecture that there is a robust correspondence between the structure of congruence lattices in varieties of algebras and the validity of systems of equations now known as Maltsev conditions. And this impression was confirmed by many deep theorems in universal algebra due to many mathematicians, including Taylor, Neumann, Baldwin, Kernesh, Gendray, Kish, and many others. So notably, in algebraic logic, we have a similar correspondence. More precisely, in 1989, Bloch and Pigozzi proved that the following conditions are equivalent for a finitary logic. So the first condition is that the logic under consideration is algebraizable. And this means that there exists a quasi-variety K such that for every member of the quasi-variety K, the lattice of deductive filters of the logic on that algebra is isomorphic to the lattice of K congruence on that algebra once we expand those lattices with inverse endomorphisms. And this property, so the fact of being algebraizable, corresponds with the fact that a certain system of rules holds. Now, of course, you don't need to absorb this system of equation right now. The only important takeaway from this observation is that in algebraic logic, there is a similar correspondence between the relation between deductive filters and congruences on one side, and the validity of systems of rules on the other side that in this talk will be called the Leibniz conditions. Now, it's important to notice that up to now, there is no precise definition of what a Leibniz condition is, and that the known ones are recognized, so to say, empirically. And the situation in universal algebra is much different. There is a precise definition of what Maltsev conditions are and what their model known as Maltsev classes are. So to make the concept of a Leibniz condition precise, we will follow the steps of what was done in universal algebra. More precisely, we will take the class of all logics and we will endow it with an interpretability relation. And then we will use this interpretability relation to characterize what are Leibniz conditions in general. So let's see, what is the aim of the talk? The aim of the talk is to investigate the poset of all logics, and this will be the poset of all possible logics in all signatures endowed with this interpretability relation. And we will use it to characterize Maltsev condition and Leibniz condition and Leibniz classes, and eventually we'll also prove that Maltsev conditions are a sort of finitary counterpart to Leibniz conditions. So let's start with the poset of all logics. In order to talk about this, let me do some quick recap from equality-free model theory. So if you take a first order theory T without equality, meaning that you don't have the equality symbol or you are treating equality as an arbitrary binary symbol, then if you take model M of the theory T, you can associate with it an indiscernibility relation, which mimics the identity. So basically, we say that two elements, A and C, in your model are indiscernible, provided that they satisfy the same equality-free types with constants. What does this mean? Well, this turns out to be equivalent to the demand that A and C satisfies precisely the same equality-free atomic formulas with parameters. So basically, we say that two elements are indiscernibles where you can't distinguish them from the point of view of equality-free logic, okay? Now, what is important is that the indiscernibility relation is a congruence on the model M, and therefore you can quotient M by the indiscernibility relation. And interestingly enough, if you compute the indiscernibility relation on this model, you get the identity. So this process of quotienting under indiscernibility, it can't be iterated. It just stops after the first application. Moreover, the quotient of M under the indiscernibility relation satisfies the same sentences without equality than M. So it's, so to say, elementarily equivalent to M from the point of view of equality-free logic. And because of that, we say that the intended models of an equality-free theory are the models of the theory whose indiscernibility relation is the identity. Now notice that this framework subsumes classical model theory. Why is that? Because if you take a classical first order theory with equality, you just rewrite equality with a new binary symbol, and you obtain an equality-free theory. Now, if you compute the intended models of this equality-free theory, you get the models of the original first order theory, okay? Now, the reason I'm telling you about this is because logics, which I'm going to define in a moment, are special cases of equality-free theories, as we will see. So let's start by saying that a logic is a consequence relation on the set of formulas of some algebraic language with infinitely many variables that, moreover, is substitution invariant, in the sense that for any set of formulas gamma and for every formula phi and every substitution sigma, if gamma proves phi, then from sigma of gamma, it follows sigma of phi. And this demand of substitution invariance is typically added to capture the intuitive idea that logics are formal in the sense that their deductions depend on the structure of the deductions and not on their content, okay? Now, logics, as I mentioned, are special cases of infinitary theories without equality. Let's see why. I mean, more precisely, one would say that you can associate with every logic an equality-free theory, and that's what we are going to do. So take your favorite logic turnstile and take a unary predicate symbol, which we will think of as a truth predicate, which claims that X is true. Now, the equality-free theory associated with the logic turnstile is the theory in the equality-free logic obtained by endo-expanding the algebraic language of the logic with the predicate P, which is axiomatized by the following formulas. So for every deduction which is valid in the logic, so if you have that gamma proves phi in the logic, then we put an axiom of this form in the axiomatization of our theory. And the axiom tells you exactly that for any assignment which makes the formulas in gamma true, this assignment makes also phi true. So as you see, this is a translation of the intended meaning of gamma proves phi. The fact that gamma proves phi means that any assignment that makes gamma true will also make true phi. So in this way, we obtain an equality-free theory associated with the logic turnstile. And we say that we call a model of our logic precisely the models of the associated first infinitary theory. And of course, these models are paired given by an algebra and the interpretation of this predicate, okay? Now, if you think in this way, if you take a logic and you view it as an equality-free theory, then the class of its intended models, as we said, is the class of models of the theory whose indiscernibility relation is the identity. And now we also close this class under subdirect products for technical reasons, okay? So for instance, if you take a substructural logic associated with a variety K of residuated lattices, the class of its intended models is given by the pairs, which comprise an algebra in the variety K and the upset of the neutral element 1, okay? So for instance, if you take intuitionistic logic, then the class of its intended models is given by the pairs consisting of a hating algebra and the top element. We will use this notion of an intended model of logic to define what an interpretation between logics is. So an interpretation of a logic turnstile into a logic turnstile star is a map, tau, that sends every n-ary connective of the first logic F, so this is an n-ary connective of the logic turnstile, to an n-ary term of the logic turnstile star. So tau of F is an n-ary term of the second logic, okay? And we do this in such a way that if you take an intended model of the second logic, then the interpretation tau allows us to turn it into a model of the first logic. Of course, to make sense of this, I should tell you what this algebra is. So what is this algebra? Well, it must be an algebra in the language of the logic turnstile. And here is the definition. So the universe of this algebra is simply the universe of A. And for any n-ary connective of this logic, its interpretation in this algebra is obtained as follows. First, we take the connective and translate it into an n-ary operation of the second logic, and therefore to a term of this algebra, okay? And then we just interpret this term into this algebra. So you should think that if the interpretation interprets this logic into this one, the transformations between the models goes in the opposite direction. So let me give you some example. Recall that the intended model of classical logics are paired given by a Boolean algebra and the top element, and the intended model of intuitionistic logics are just given by pairs consisting of a hating algebra with the top element. So then the identity map is an interpretation of intuitionistic logic into classical logic, because think that this is classical logic and tau is the identity map. So then you take an intended model of classical logic, which is a Boolean algebra plus the top element. And when you compute this structure is simply A, because tau is the identity. So what you get here is again Boolean algebra plus the top element. And clearly this is an intended model of intuitionistic logic because Boolean algebras are hating algebras. Now you might wonder whether the converse is also true. So is it possible to interpret classical logic into intuitionistic logic? Well, in this sense, the answer is that no, it's impossible on cardinality grounds. Let's see why. Suppose for a second that you can interpret classical logic into the intuitionistic one. And then you must be able to translate the intended models of intuitionistic logic into those of classical logic. So take, for instance, the intended model given by the 3-element hating algebra plus the top element. Now you must be able to turn this algebra into a Boolean algebra using some interpretation tau. But notice that interpretations won't change the cardinality of the algebra. So basically, if there were an interpretation of classical logic into the intuitionistic one, you must be able to construct a 3-element Boolean algebra. And of course, this is impossible because there is no 3-element Boolean algebra, fortunately. All right. So now the interpretability relation is a pre-order on the proper class of all logics in all possible languages. and we take the associated partial order and we term it deposit of all logics. Its elements are equivalence classes of equi-interpretable logics. And notice that equi-interpretability is a much weaker notion than term equivalence, okay? What is important to observe is that deposit of all logic is not a set. Its universe is not a set because it's obtained by quotienting the proper class of all logics, okay? This will become important in a moment. So let's begin by studying some properties of deposit of all logics ordered under interpretability. The first natural question is whether this poset has infima. And the answer to this question will be positive, as we will see in a moment. So take a family of algebraic languages, which are possibly different. We can merge them together into a single new algebraic language as follows. So we say that a basic n-ary operation of the new language is just a sequence of length I of n-ary terms of the various languages, okay? And then given a family of algebras such that AI is in the language Li, we can put this algebra together into a new algebra in this language. So the universe of this algebra is the Cartesian product of all these algebras. And the interpretation of an n-ary operation like this one in this algebra is obtained as follows. So take n elements into the Cartesian product. And remember that this thing should be a sequence in the product. So we just need to say what is the value of this sequence on the ith coordinate. Well, and the answer is pretty easy. We just look at f and look at its ith coordinate, and we get an n-ary term of the language Li, and we just compute phi I on the ith projections of the arguments inside the algebra AI, okay? Now we can use this construction to define a logic in the following way. So the non-indexed product of a family of logics, possibly in different languages, is the logic induced by the classes of models, which are obtained as follows. We just pick intended models of the various logics, and on the algebra part, we take these new algebra, and on the predicate part, we just take the Cartesian product of these predicates, okay? And what one can prove is that the infimum of the family of the logics ternstile I is precisely this non-indexed product. So what we obtain is that in the poset of logics, infima indexed by arbitrarily large sets exist. On the other hand, we can wonder whether suprema exist, and one can prove that even binary suprema fail to exist. Now notice that this is a peculiar situation, because normally if you have a poset and you can prove that it is a complete mid semi-lattice, then the poset is automatically a complete lattice. But the proof of this relies on the fact that the universe of the poset is a set. And since this is not a set, we cannot replicate this kind of argument. And we will see that even binary suprema might not exist. So the proof is combinatorial and a bit involved, but I can just tell you what is the solution. So if you take the negation fragment of classical logic, which is the logic axiomatized by the rules that say that x and not x are interderivable, and that the x falso sequitur quadruped rule holds. And then you take also a new algebra, which is a joint semilattice, the following joint semilattice with certain constants. And you take the logic induced by the models obtained by endowing A with this singleton and this subset, and you call it L. Then the join of the negation fragment of classical logic and L does not exist in the poset of all logics. The reason being that if this join would exist, then its language would be a proper class. You might wonder if this problem can be accommodated just by allowing logics to be formulated in languages which are proper classes, or bounding the size of languages of logics. And the answer is that it's not obvious that this would resolve the problem, unfortunately. All right, now I would like to tell a few words on how you can use this order theoretic framework to make precise the notion of a Leibniz class and the Leibniz condition. So remember that the Leibniz hierarchy is a classification of logics in terms of systems of rules, which we will call Leibniz conditions, that somehow govern the interplay between deductive filters on one side and congruencies on the other side. So in this talk, a Leibniz condition will be a sequence of logics indexed by all the ordinals. So this is a proper class in general, which satisfy the following requirement. So if you have an ordinal alpha, which is less than or equal to an ordinal beta, then the logic indexed by beta is interpretable into the logic indexed by alpha. So here comes a picture. So this is the poset of all logics, okay? What is a Leibniz condition? Well, it's a descending sequence of logics in the interpretability order indexed by all ordinals. So all these things together is a Leibniz condition. And we say that a logic satisfies the Leibniz condition phi if at least one of its members, ternstile alpha, is interpretable into our logic. And we will say that the class of models of the Leibniz condition is just a class of logics that satisfies the Leibniz condition. Now, what is that semantically? Well, it's just the upset into the poset of all logics generated by the infinite descending chain, which is the Leibniz condition. So basically, you can think as Leibniz condition as infinite descending chains into the poset of all logics, and those are generators of a certain upset, and that upset would be the class of models of that Leibniz condition. Moreover, we will say that a Leibniz class of logics, we will say that a class of logic is a Leibniz class if it has the form mod phi for some Leibniz condition. So Leibniz classes are the classes of models of some Leibniz condition. And one can prove a theorem stating that Leibniz classes are essentially the set complete filters in the poset of all logics. So basically, a class of logics is a Leibniz class if it's closed under non-indexed products and interpretability. That's the idea. Interestingly, in order to prove this result, it seems that you need to use the foundation axiom of set theorem. So let me give you some example to make this a bit more concrete. A logic is said to be proto-algebraic if there exists a set of formulas in variables x, y, and possibly some parameter z that define the indiscernibility relation. This means that for every model of the logic, we have that two elements of the model, A and B, are indiscernible if and only if for any choice of parameters in A, delta of A, B, and C belong to F. Okay, so essentially, this set of formulas allows us to define indiscernibility. And when this sequence of parameters is empty, we say that the logic under consideration is equivalential. Now, proto-algebraic logics form a Leibniz class determined by the following Leibniz condition. So we have a class of logics indexed by all ordinals, and on the ordinal alpha, the logic that we consider is the following. So the language of the logic is given by alpha many binary connected, which I'm denoting by this strange implication. So let delta alpha be the set of formulas x implies y for all these possible implication connectives. Then this logic is the logic axiomatized by this system of rules. On the one hand, we have the rule telling us that delta alpha of xx is a set of theorems. And on the other hand, we have modus ponens formulated for this set delta alpha. So this is a Leibniz condition, and the class of its models is precisely the class of proto-algebraic logic, and therefore the class of proto-algebraic logic is a Leibniz class. And similarly, one can prove that equivalential logics form a Leibniz class. Now, one of the things that I find appealing of this presentation of Leibniz conditions and classes is that this ordered theoretic framework allows us to formulate in purely mathematical terms some semi-philosophical questions. For instance, you can ask yourself the question of which Leibniz classes are fundamental or primitive. Why is that? Because the order theoretic language gives us a precise way to talk about the fact that a condition is fundamental. More precisely, you can think that a Leibniz class is fundamental if it is irreducible in the lattice of all Leibniz conditions. So basically, a Leibniz condition is fundamental if you can't write it as the intersection of two strictly weaker Leibniz conditions. Or perhaps you can say that it's fundamental if it is determined by a Leibniz condition whose elements are irreducible or perhaps even prime in the poset of all logics. Okay. Now, these two notions of being fundamental are not equivalent. For instance, the Leibniz conditions that determine the classes of proto-algebraic and equivalential logics consist of logics that are prime in the poset of all logics. So from this point of view, proto-algebraicity and equivalentiality are fundamental conditions. On the other hand, you can prove that the Leibniz classes of proto-algebraic or equivalential logics are not irreducible in the lattice of all Leibniz classes. So you can write this condition as intersections of weaker conditions. Okay. So before looking at these decompositions, let me mention a few Leibniz classes which are prime. So of course they are also irreducible, that they can't be written as the intersection of two weaker things. So first, logic with theorems, they form a Leibniz class which is prime in the lattice of all Leibniz conditions. The second is the Leibniz class of truth equational logics. So remember that a logic is said to be truth equational if there exists a set of equations tau, such that whenever I take an intended model of the logic, the truth predicate f can be defined using tau, in the sense that f is the set of solutions of tau in the algebra A. So the truth equational logics form a Leibniz class, which moreover is prime. And similarly, the class of assertional logics form a prime Leibniz class. So remember that a logic is assertional if there is a constant term 1, such that for any intended model of the logic, the truth predicate f is just the singleton of 1. So this is the case, for instance, for classical and intuitionistic logic or substructural logics with weakening. Okay, all these are prime Leibniz conditions. And moreover, actually, the class of assertional logics is a principal filter in the poset of all logics. It is this means that there is a least assertional logic, which is basically a logic of pointed sets. That's the idea. Now, as I said, unfortunately, the Leibniz classes of proto-algebraic and equivalential logics are not irreducibles, and here comes some decompositions for them. So first, take the logic BA determined by the class of models whose algebra part is a Boolean algebra and such that f contains the element 1. Of course, f need not be a filter. It just need to contain 1, and therefore this logic is not classical logic. And let K be the class of logics in which PA is interpretable. Okay? This is a Leibniz class. And one can prove that the class of proto-algebraic logic is the intersection of the following larger Leibniz classes. First, the least Leibniz class containing proto-algebraic and assertional logic. And second, the least Leibniz class containing K and all proto-algebraic logics. The way you prove these results is combinatorial, and it relies on some model theoretic description of proto-algebraic logics. So it's a mixture between theorems on proto-algebraic logics and combinatorics. You can also prove that the class of equivalential logics is not irreducible as follows. So we say that a theorem of a logic is injective if its interpretation is injective in all the intended models of the logic. Of course, we are assuming that the theorem is just in one variable. Okay? And one can prove that the class of all logics with an injective theorem is a Leibniz class. Now, the class of equivalential logics is the intersection of the following strictly larger Leibniz classes. On the one hand, the least Leibniz class containing equivalential logics, of course, and proto-algebraic logics with an injective theorem. And second, the least Leibniz class containing equivalential logics and proto-algebraic logics that moreover are assertion. Okay. And now getting close to the end, so let me just make some connection with Maltsev classes. In order to do that, I need to introduce some finitary counterpart of Leibniz conditions. To do that, we say that a logic is finitely presentable if its language is finite and the logic can be axiomatized by a finite number of finitary rules. This means that you have a finite presentation of the logic. So one can prove a theorem, which is a generalization of a result of Neumann, which was first established for varieties 2 logic, stating that if you take 2 logics that are finitely presentable and finitely equivalential, this latter assumption means that the logics are equivalential and that this set delta defining the indiscernibility relation can be taken to be finite. So if you have 2 logics that are finitely presentable and finitely equivalential, their non-indexed product is term equivalent to a logic which is both finitely presentable and finitely equivalential. So Neumann theorem, the original theorem stated that the non-indexed product of 2 finitely presentable varieties is term equivalent to a finitely presentable one. The logical version of the theorem shows you that you need the assumption of finite equivalentiality in the theorem, which was implicit in the algebraic theorem. And the reason why you need it is that the theorem does not hold for outside the framework of finitely equivalential logics. You can build up a graph theoretic argument showing that the non-indexed product of the following 2 finitely presentable logics is not even equi-interpretable with anything that is finitely presentable. And the 2 logics are the logics of the ex falso sequitur quadlibet rule. And the second logic is the logic of the rules from box X, it follows X. Now, what is a finitely presentable Leibniz condition? Well, this is a sequence of logics indexed by the natural numbers, this time not all ordinals, and these logics are finitely presentable and finitely equivalential. And moreover, if a natural number n is less or equal than the natural number m, then the logic indexed by m is interpretable into the logic indexed by n. And we have that a class of logic is a finitely presentable Leibniz class precisely when it is the class of models of some finitely presentable Leibniz conditions. Now with this toolkit at the end, we can explain the relation between Leibniz and Maltsev classes. So first, we discussed the framework of logics, but all this can be extended to 2 deductive systems. Those are just substitution invariant consequence relation on the set of equations of some language. So you just replace formulas by equations. And in this setting, we have that a class of varieties M is a Maltsev class in the sense of universal algebra, if and only if there is a finitely presentable Leibniz class L of 2 deductive systems, such that the Maltsev class is the class of all varieties whose relative equational consequence belongs to the Leibniz class. So in this sense, what we get is that Maltsev classes are nothing else than the restriction to varieties of finitely presentable Leibniz classes of 2 deductive systems. And this now explains the relation between Maltsev and Leibniz classes. You can think of Maltsev classes as some finitary counterpart of the infinitary Leibniz classes. I think there are many things to say, and many of the things that one can ask in this setting are still open problems. So it's better for me to stop here, and thank you very much for your attention.
Thanks, Tommaso. Your talk was very, very stimulating, and as I predicted, we are flying very, very high in the hierarchy of logics. Or very, very low, depending on which way you. I like to look at things staying on my head, so it's like being an algebraist. So I think those things are very, very high in the hierarchy. So the more incomprehensible they are, the higher they are. So that's my classification. Okay, now that we should have a discussion. And first, let me say that of course, Nick Galatos cannot be here because, I mean, he's 8 hours behind in Denver and now he's teaching a class. So I have to excuse him and you'll have to excuse him too. Now, first, I mean, are there any questions related to the talks? I mean, talks were very different. So I suppose that if you have questions. So I don't see any direct questions. So I mean, let me start by saying that, you know, here we really have seen some, you know, cross section of what we are doing in modern algebraic logic, right? Because we have seen very, very different things. I mean, we have seen 3 talks that are so different one from the other that, I mean, they might not even belong to the same field of mathematics. Because we have seen first a purely algebraic talk by Nick Galatos, in which, I mean, we are really dealing with structure that have a certain precise signature, and we are just, you know, beating the shit out of them, you know, if you pardon my French. And in the second talk, we have seen an example of the connection between logics and their algebraization, and the fact that you can express logical properties algebraically and conversely algebraic properties in a logical way. Well, sometimes this connection is not, you know, so fruitful, in the sense that you might get an algebraic concept that certainly has some translation in logic, but this translation is not particularly significant. But of course, the other way around happens too. I mean, there are many logical concepts that sort of trivializes in the algebraic representation. And this is mainly due to the fact that, you know, the semantic complex is always structural. So, I mean, you always sort of lose certain, in particular, I mean, as we say that, you know, algebraic semantics is very good for talking about things, and relational semantics is very good for talking about proofs. Because, I mean, in the algebraic semantics, you always lose this connection. So what is the idea behind this? Well, what I wanted to do was to present the various phases of what we are doing now in modern algebraic logic. And the idea is that all these things are connected. I mean, they don't seem connected, but they are. In fact, I mean, I could, for instance, totally rephrase Thomas Moraschini talking in my algebraic language, and I mean, because he has said things that, in a way, I've already said in my talk, only in a slightly different way, and the same for Sarah's talk. I mean, and the same for Nick Galatos' talk, because I mean, I can talk about the logic of distributivity, of distributive lattice ordered monoids, right? And this is the logic that probably is a distributive logic that has some characteristic, and probably, I mean, if we start looking into this, we could find something interesting. I don't know, but this is what we do actually, right? This is what we do. Now, I would like to also the other people who talk to express their ideas about it. So, I mean, at least we can have, so the people who are listening can have an even clearer idea of what we are doing now. Carlos, you want to be the first?
So you mean that's some precise question?
No, I just want you to talk about, you know, to elaborate on what I said. I mean, that the fact that, you know, things that seem so different are in fact various aspects, various facets of the same concept, which is, you know, basically applying algebra to logic or logic to algebra, whatever, right?
Yeah, that's right. Well, you have expressed it very well. Sorry, in this moment I don't know what else I should add.
It looks like I preempted all the. Tommaso, you want to add something? I mean, I'm particularly interested.
I have a tangible, slightly more concrete question for Sarah. I don't know if this is the right moment where to ask.
It is always the right moment to ask concrete questions.
So my question is this one. Yeah, I always struggle to understand what is the algebraic counterpart of Halden's completeness. At least assuming that this property can be formulated in general enough so that it becomes the theorem, say, of abstract algebraic logic. So after your talk, I have the following impressions. So is it possible that one might phrase a version of Halden completeness as follows? Something like this. I'm not claiming that this is the right way, right? So on the logic side or on the equational logic side, you can think that if gamma, you have two sets in these joint variables, delta and delta prime, okay? So if from gamma and delta, you can prove something, and from gamma and delta prime, you can prove the same something, then this something can be proven from gamma. Maybe this seems a sort of metalogical abstraction of the Halden completeness. So my question is it possible to, do you think it's conceivable that one can prove a bridge theorem stating that, say, in algebraizable logic, maybe even a proto-algebraic logic, but let's stick to algebraizable logic. An algebraizable logic satisfies this Halden completeness principle if and only if the quasi-variety associated with it is generated as a quasi-variety by maybe finitely relatively finitely subdirected reducible algebra, something like this. And the reason why I believe that maybe this is possible is because you can do something with another variable sharing principle, which is basically equivalent to the demand that the quasi-variety is generated by a single algebra has a quasi-variety. So maybe this Halden completeness can be a strengthening of this other one if one formulate it in general enough. I don't know if you think, my question is if you think that something like that is possible.
I see what you're saying, and I mean, my answer is just maybe. I don't see any reason why they would not be possible as of right now, but I think your intuition is probably, I mean, makes a lot of sense, because I was actually, when I was preparing these slides, I was thinking if I would phrase this, more talking about these variable separation properties that you have and these connections between logic and algebra. So I do think that this is worth looking into it, but I cannot give you anything more than it. But I think it's surely very reasonable to look at it that way, because actually some of the very interesting connections between logic and algebra are exactly of this kind, right? When you can when you can identify these properties where you don't where there's these variable separation properties acting on the generating algebra. So yeah, I had not answered to your question right now, but I do think it's possible.
I may give some algebraic insight if you like.
Mm-hmm.
Okay, what we are basically using on the to prove these theorems are a couple of basic facts of universal algebra, mainly the Birkhoff theorem for varieties and the Johnson theorem for varieties, right? And they both have an equivalent for quasi-varieties, okay? Due to Szelakovsky and Pigozzi and whatever. I mean, but there are equivalents to these theorems for quasi-varieties. And so I have no, I mean, I do believe that your intuition, if of course stated in the most correct way possible, because, you know, I mean, you know, as the late Franco Montagna used to say, right, you can't prove almost anything as long as you have the proper definition. So we first should strive to formulate the question in a way that we can answer it, because this is the real trick, right? I mean,
I think part of the problem is to formulate a general enough version of the Halden completeness property. So a slightly related question is, it seems that there was some motivating theorem by Ono, am I right?
Ono and Kihara, yes.
Ono and Kihara, yes. So in that case, one of the conditions is that the variety under consideration is generated as a variety by a well-connected algebra. So can one improve this by saying that the variety is generated as a quasi-variety by a well-connected algebra? Is there any chance that one can do that? in that theorem. So if that's possible, then maybe one is likely closer to getting something like this.
That's a very interesting point. Of course, I mean, we do not have an answer on top of our head, but I mean,
no, because we
that is certainly what
proof again, of course, because there are a lot of technical details on the proof, so it's hard to grasp exactly what is needed.
But I mean, I agree with you. It's an analysis that we should perform. I mean, we should actually go through the proof and see what is really needed, because sometimes you inadvertently prove more than you think.
Yes.
That's
also now I wanted to do these connections, right, between algebra and logic and take the focus on that. But what we actually started from is characterizing joint reducibility, right? So we were starting from there and see how we could characterize that logically and by degenerating algebras. So, but now rephrasing this, starting from Alden completeness, of course, a lot more questions come out, right? And this is one of the other interesting things that this approach has, right? That if you try to turn things around, then you may get more questions. And actually, your questions are really good ones.
Yes, but
are also very natural, even. But
let me state that there is a snag here. Because you see, the difference between varieties and quasi-varieties is this one. Okay, we do have the same kind of theorems, but the problem is that for quasi-varieties, the theorems are stated using relatively subdirectly reducibles, right? Now, while the concept of being subdirectly reducible is an absolute concept, I mean, an algebra, you can tell if an algebra is a geometrical property. You look at the congruous lattice of an algebra, you can tell if it's subdirectly reducible or not. If it has a unique minimal element, it is subdirectly reducible, otherwise it is not. But the concept of relative subdirectly reducible depends strongly on the class of algebras you are considering. So you have no absolute definition, and this complicates things a lot. And I mean, I've been studying quasi-varieties lately, you know, quasi-varieties of residuated lattices, of course. And I mean, that's the main problem. That you cannot, and then again, what you are asking is basically, can we characterize joint irreducibility or strict joint irreducibility in the lattice of sub-quasi-varieties of a quasi-variety or a variety, whatever? Can we? I mean, I'm not so sure because
I'm gonna, yeah, I'm sorry.
Because, you know, lattices of quasi-varieties are very, very complex in general, way more complex than lattices of sub-varieties, and you know that very well because you know what, you know, the concept of Q universal and stuff like that. So I mean, they can be very, very complex. So certainly something that it is worth pursuing, but my general opinion is that we should start even lower, because we do not have a real understanding of lattice of quasi-varieties, not even in the simple cases, right? Yeah. We have no idea actually. I mean, if I may continue, if we look at the lattice of quasi-varieties of very friendly, very, you know, amenable algebras, like say Weisberg-Hoops, right? Now, the lattice of quasi-varieties of Weisberg-Hoops is Q universal, which means that the free lattice over countably many generator can be embedded into it. So, which means it's complex beyond any possibility. And we don't know much about this lattice of sub-quasi-varieties, even in this very, very, very friendly case. Actually, we know quasi-varieties generated by chains, and we know something else, but I mean, we don't know nearly enough. And we are talking about a very, very friendly kind of algebras. So if you go to more general cases, I mean, you might have to face problems that have not been even described yet. So, I mean, it's an ambitious task.
Yeah, my only point was that I mean, the fact that the quasi-variety is generated by a single member as a quasi-variety corresponds to a metalogical principle, which involves somehow some disjoint sets of variables. I was saying maybe you can even make, if you strengthen this metalogical principle, you can force that algebra to be relatively finitely self-directly reducible. Anyway, I didn't want.
No, I mean it's certainly. Look, I mean, it's a very stimulating question, and believe me, we are going to think about it. We are going to think about it. That's for sure.
Okay, thank you very much.
Yeah, I think we're gonna break. I think I don't think this is going to reflect on the lattice of subvarieties for which this connection is really, you know, based off the fact that you can characterize the congruence filters. I think you're gonna break this link, you know, between being able to control the subdirected reducibles and, you know, how they look like, because some of these proofs really construct, right, what's going on in a subdirected reducible algebra. So I think the link with the lattice of subvarieties would be broken, but I do think it makes sense to study the logical property of Alden completeness with respect to generating algebras of the varieties. I think this is really reasonable for sure. But yeah, thank you for this suggestion.
Yeah, thank you very much. I would definitely be interested in this. Thank you.
Mm-hmm.
I had another comment, if I may, related to Sarah's talk, also aiming at generalization, but much more modest than Tommaso's idea, much more. No, but I was just thinking about, if I understood, I don't know. When you considered this, what you call the condition G for Galatos, I thought, well, the purpose of that was to obtain that the number of conjugates that you have to involve is actually finite.
Yes. Yeah, it's kind of that. Yeah, so the fact is that you see, he elaborates this algorithm, right, that generates this equational basis for the join of varieties. And the thing is that you really need to include all these joins of iterated conjugates, and infinitely many. But if one of these conditions holds, you can stop at just iteration n.
Yeah, and this was key, no, for some of your results. When there was this stopping at some finite level, then you could obtain some of your theorems, right? So this made me think that maybe some level of generalization you could obtain easily is to what we have studied together with Peter Cintula, what we call the finitely disjunctional logics. Logics that have a disjunction in this sense of a disjunction defined by a set of formulas that all together behave like having the proof by cases. Because in those substructural logics that you were dealing with, the set you were defining given by lattice disjunctions of results of operating the conjugates on each term, we know it gives a generalized disjunction in our sense, and in that case it would be given just by a finite part of your big set, which is the notion we call finitely disjunctional. So I don't know how much your proofs are attached to the particular language and the particular properties of those substructural logics. But if they are not so much, then maybe that would hint that you could generalize some of the proofs to at least this level of finitely disjunctional logics. I was wondering.
I think that's for sure also possible, because really you don't really need it. We don't really use the language, right? We really use these properties of the disjunction, essentially. Now you axiomatize using these junctions, actual lattice operations, if you want the order, maybe. How you can use that to axiomatize the join of varieties, right? So yes, I really don't.
That was my feeling, that at least you could get this level maybe almost for free.
Yeah, probably. But then again, you have to be careful about the algebraic counterpart. I mean, what really is.
Yeah. So in contrast with what Tommaso was asking, maybe here you can have a connection between these properties and the subvariety lattice, and maybe not so much, of course, with generating algebras. With there you go back to the residual lattice structures, right? Okay. So, but yeah.
Okay, thanks.
Thank you. Yes.
Okay. Well, I mean, it was a very nice discussion. I mean, I'm glad that this paper gave rise to, you know, interesting observations, because I mean, we spent a lot of time writing it.
It's actually not that long, honestly.
Well, I mean, I don't know.
It
seemed forever. I mean, it seemed forever, really. But still, I mean, it's because of all the technical details, of course. I mean, as I told you, this is very technical. So, but probably maybe this suggestion can help us in simplifying also some of the techniques. I mean, sometimes if you look things from a higher perspective, I mean, you can see things more clear.
I like your paper. It's AAL in the old fashion that I understand and I like very much. But then what we have seen with Tommaso takes things to a whole different level, and I was feeling a bit dizzy. Like, okay, Tommaso is writing the next chapter of abstract algebraic logic, and and I was impressed, and I would need time to process it for sure. But can I ask some very naive questions to start, Tommaso? So your Leibniz classes, the way you have defined them, are all the classes in the so-called Leibniz hierarchy Leibniz classes? Because you mentioned only 2 examples. I think you said proto-algebraic logics are and equivalential are. Also the others, or maybe you said it and I missed it. Sorry.
So let me first start by saying that this is not something that I invented. So this is something that basically was there in universal algebra. So in universal algebra, to define what a Maltsev class is, you just take all varieties, order them and their interpretability, which is much easier in that sense. And basically these varieties, well, equivalent classes of equi-interpretable variety form a lattice, and then you study certain filters, which are just these finite representable filters, are the Maltsev classes. So this is inspired by the clever ideas of Taylor and others. So basically, I would say that all the classes that I know that are in the intuitive Leibniz hierarchy are also classes in this hierarchy with the following small caveats. So one is that finitely equivalential logics or finitely algebraizable logics are not Leibniz classes, but they are finitely presentable Leibniz classes. So not every finitely presentable classes are not Leibniz classes in general.
I guess this will be the case of weakly implicative logics as well, right?
It depends. So basically, no, I think weakly implicative logics would be a Leibniz class in the standard sense. So as soon as you require something to be finite, then your class would be finite.
In weakly implicative logic is finite in the sense that we're speaking about just one particular connective.
One is fine.
I see.
One is fine, but if you have finitely many of increasing size, basically you need to have these. When you need to have a limit, basically, yeah. Then you would need to allow the omega case. So one is fine. So I think the class would be a Leibniz class. But for instance, if you would say finite set, then this would become a finitely presentable Leibniz class.
I see.
And the other thing is that logics with an algebraic semantics, meaning that they just have an equational completeness theorem, they are not algebraizable, these are not a Leibniz class, basically because they are close under non-indexed product, but they are not close under term equivalence. So basically they are not close under equi-interpretability. So this is I would say the only class that I know to be associated with the Leibniz hierarchy, which is not a Leibniz class, which is also good because it's a very poorly behaved class, basically.
And more naive things. If you take a particular logic and take
the last question, because we are running out of time.
Sorry. I don't know, so maybe somebody else want to ask something. No?
No, go on. We have 3 minutes.
Okay. So if you take a particular logic, Tommaso, and you consider all its axiomatic extensions and stuff like that, this also fits well in your notion.
Yes. If you fix a logic, well, every principal upset basically in the posit of a logic is a Leibniz class. So if you fix a logic and take all the logics in which there is logic interprets, this is Leibniz class, and it's the least Leibniz class that contains it, of course. This class will contain all the extensions, possibly infinite extensions of the logic, but many other things, right? Because the logic is typically equi-interpretable, even with many things that are strange, right? That that may not be, well, not have the same language, basically.
Yeah, sure, yeah.
So yes, if you take logic and take the Leibniz class generated by it, it would contain all the extensions of that logic. That's correct.
Okay. Well, all good things come to an end, and I mean it's time to close this session. I mean, I thank Nick Galathos, Tommaso Moraschini, Sara Golini, and Carles Noguera, and myself, of course. And I mean, it was fun. It was fun, and thanks, Melania, for asking me to organize these things. I mean, it's it was very fun to have it. So, Melania, you want to say something as an organizer? You're okay.
Sorry, first me, probably after that, Professor Hounkonnou. Thank you very much, Paolo. I have did it on behalf of organizing committee. I was delegated because Professor Hounkonnou and me vote. And the result is his vote is apparently me to communicate with you. So yeah, it is done. Of course, everything is done. Is joint job by him and me, and now I'm talking. As I assume Professor Hounkonnou will say something after me, right or not? I don't know, right? Right. So thank you very much. Yeah, it was a very, very interesting journey through the logic and through applications of algebra within logic. Due to you, I can say, because when we prepare this and talk about this colloquium, you explain to me your idea. So I can tell you that that you gave me idea to present constructive semigroup with the partners in a similar way. So tomorrow will be a small kind of colloquium, whatever, on constructive semigroups done in this model. So first, a general story about what we achieved during last year, then some special, very interesting and very complicated result, but what is not complicated in mathematics. So yeah, thank you very much. Thank you very much for your acceptance. Thank you very much for ideas you share.
You're welcome. You're welcome.
Yeah, thank you very much to presenters. Especially, I'm impressed by, of course, we how to say, we are not. I'm searching for the right words. Especially, I'm impressed by lectures given by a young part of your team, and especially we all the little bit old, right? We have experience, we are professionals, so it's almost normal for us to present in a very good way. But all congratulations to Sara and to myself for that. I think they deserve. Of course, Charles, I don't know. You are older.
We are.
We are experienced. No. We are experienced.
we have more experience. Certainly, we have a lot more experience.
It is better to put this in such context. So, what to say? I wish you are here. I wish you join us, because when we stop with this and when we, how to say, turn off the light of the camera, we are going to the restaurant. I wish you were here, but I do hope, especially I promised to Sara and Tommaso, I think in my name and the name of Professor Hounkonnou, that as soon as our, how to say, doctors, policymakers, whoever, told us and officially announced that Corona is finished, then we will consider possibility and organize something here live in Niš. To start again in Niš, and later we will see. We will only remind that is tomorrow start at 10. We will back to 10. Professor Hounkonnou?
Yeah, I'd like to join my voice to the voice of Professor M.Mitrović to address our thankfulness to the chair of this colloquium and to congratulate all speakers for the rich, wonderful talks. We learn a lot because this field is very new for me, and many interesting things you talk about. Really, I enjoy your talks. I enjoy the discussions. I enjoy the open questions you raise, and we hope you will contribute chapters to the book which will be published by Springer in very nice way. So again,
okay, that was what I wanted to have. So I mean, I'm glad my message got through somehow. Okay.
Yeah.
So I think we can say see you tomorrow.
Oh.
See you tomorrow. Yeah.
What?
Or to stay online and to have some inside in Niš restaurants. Right, it is good to be alive in Niš.
Okay, but
by night. Oh, Paolo, you experience a little.
Yes. I've been in Niš almost a week, and it's been a very nice week. I'm looking forward to do it again, actually.
Yes.
Especially
I have to say goodbye.
Yeah.
First of all, I have some trouble with my camera. I don't know why, but I would say goodbye because tomorrow I'm going to Poland to participate in another workshop in Warsaw. So thank you very much. Goodbye, everybody, and hope to see you once again.
Careful. Have a nice trip.
Thank you.
Thank you for being with us, Richard.
Thank you very much. I don't know what happened with my camera.
Now you are upside down.
Now you are
upside down.
My computer.
Now you are sideways.
Sorry, I should be like this.
Okay.
Yeah. Okay.
Bye.
Bye.
Thank you.
Okay. So
au revoir.
I would say it's time to call it quits. So goodbye, everybody. See you tomorrow. Bye.
See you tomorrow. Yeah. Bye.
No.